Night drapes the observatories, and the instruments keep their vigil. Photons skip across mirrors. Atomic clocks murmur in their tiny throats. Cryogenic sensors breathe shallow and slow. In that hush, a different brightness gathers, the brightness of ideas that stretch beyond the reach of lasers. At this edge of knowledge, theory begins to outrun light. Equations move where detectors cannot follow, slipping across horizons that machines cannot cross. The cosmos still shines, yet a deeper veil hangs inside the shine, a threshold where certainty thins and guesswork, disciplined by mathematics, takes the first cautious step. Hearts of stars collapse into pits of gravity, and in those pits the classical map splinters. Einstein's geometry curves cleanly through galaxies and planets, yet near a black hole's heart, space bows so sharply that the map tears. Quantum rules whisper of jitter and chance, of fields that foam with fluctuations, of a world built from quanta that disobey classical certainty. Two languages speak at once, and both are true within their provinces. Between them, a silence opens, not the silence of ignorance, but the silence that follows when two accurate sentences refuse to combine into a paragraph. The smallest scales taunt with a number, the Planck length, so tiny that the mind reaches for metaphor and returns empty-handed. At that scale, gravity and quantum fields are expected to wrestle for primacy, yet experiments cannot enter the ring. Energy requirements balloon beyond any collider, distances shrink past any probe. Nature seems to guard its primal blueprints with a barrier that is not iron or stone, but sheer diminishment. To approach is to lose grip. Precision flips into uncertainty, and uncertainty becomes the only reliable signpost. Within that frontier, infinities bloom like alarms. Calculations diverge, integrals refuse to settle, and singularities mark locations where the equations run out of breath. Each infinity is a riddle with teeth, less a number than a warning. It says that a faithful description has wandered into a country where its passport is not valid. Physicists do not accept infinities as answers. They treat them as messages, red script in the margin, urging a revision of the story that generated them. Black holes crystallize the challenge into an emblem. Nothing else gathers so much certainty and doubt in one place. Their masses and spins parade across the sky with quiet authority, confirmed by orbits and by waves of space that ring like struck bells. Yet at the horizon, a subtler question arises. If quantum fields flicker there, if particles seep outward as thermal light, then bits of history might drift with them. A ledger must exist, or a ledger must be erased. Both possibilities trouble the mind, for one seems to violate quantum law, and the other seems to mock the geometric clarity that made gravity elegant in the first place. Entanglement threads through this puzzle like an invisible fibre. Two particles share a state, and distance does not sever the bond. It is a correlation without a signal, a pattern without a push. In the background hum, the relations matter more than the objects. The network begins to resemble the thing it once merely described. Many suspect that geometry itself may be woven from such correlations, a fabric stitched by information, where area counts and volume remembers. If that hunch holds, then gravity might be less a force than a bookkeeping of connections. At the edge of testability, beauty becomes both compass and mirage. Equations that close with effortless symmetry invite trust. The mind recognizes harmony with the same quiet pleasure it finds in a well-tuned chord. Yet, history offers caution. Beautiful theories have dazzled and then dimmed when confronted by stubborn data. The craving for elegance animates discovery, and it can mislead. The task at hand is to let beauty suggest and let nature decide. A garden of frameworks has sprung from this tension. Some stretch the notion of particle into string, then into brains, and finally into spaces of many curled dimensions where vibration replaces point-like collision. Others quantize geometry itself, counting the quanta of area and volume, letting space become granular and time become a procession of relational changes. Some recast locality as an emergent illusion, replacing objects with algebra or with orderings of causal influence. Each framework writes a different grammar for reality, and each promises to calm the infinities that shouted in earlier attempts. The question of evidence presses from all sides. Detectors strain for whispers that might betray a deeper structure. Gravitational wave observatories sweep a new band of the cosmic spectrum, hoping for faint signatures from the first instance of expansion. Polarization maps of ancient light stare into a relic fog, looking for patterns sketched by primordial ripples. Laboratory experiments cool macroscopic objects to the border of quantum behavior, then listen for the faint tug of spacetime on their coherence. The threshold between dream and demonstration remains narrow but not motionless. Amid this search, the human rhythm continues. Chalk dust floats in seminar rooms where arguments sharpen and soften with the hours. Coffee cools beside notebooks heavy with symbols. Computer clusters churn through landscapes of possibilities, pruning, fitting, refitting, discarding. Older voices remember earlier fashions, and younger voices insist that a new synthesis stands just out of frame. The mood is neither despair nor certainty. It is patience set to the tempo of curiosity. Causality itself flickers under inspection. If quantum processes appear to shrug at ordinary order, then perhaps order is not primitive. Perhaps sequence is born from statistics, and distance is born from webs of inference. This is not a claim of magic, but a proposal that the cosmos economizes in ways that human intuition, trained on friction and sunlight, does not expect. Under that view, time is less a river and more a ledger of changes that have successfully knitted into consistent histories. Thermodynamics sends its sober telegrams into this conversation. Entropy climbs, information disperses, and the past differs from the future in a way that experiments can weigh. If gravity participates in these imperatives, then curvature may respond to the counting of microstates, and horizons may acquire temperature because information is trapped and rearranged. Then geometry would be the outcome of statistical bookkeeping, not a starting point. The weight of a world would tally the hidden degrees of freedom that sustain it. Risk accompanies every attempt to climb beyond current tests. A theory can be too general, swallowing contradictions without translation into prediction. It can be too specific, selecting an elegant corner of mathematics that nature never visited. The discipline lies in the framing of questions whose answers could, in principle, be heard within a lifetime. That discipline is not only technical, it is ethical in the small sense, a promise to separate longing from logic. Reason does not stride alone. Imagination outlines possibilities that reason then trims. The enterprise resembles art in that pattern seeking, and it resembles engineering in its demand for confirmation under stress. The strange conjunction of solitude and collaboration continues, a hum that links continents. If the smallest scales remain hidden for now, the largest scales continue to speak, and in that speech the hints accumulate. Patterns in sky maps, echoes in the gravitational spectrum, anomalies that refuse to wash out. Each is a shard that might fit a wider mosaic. Through it all, a simple feeling persists. The world is intelligible, and the world is not fully understood. That tension carries the pulse of the entire project. It lends gravity to the details and lightness to the long wait between signals. The unknown here is not a void but a reservoir, a place where questions gather pressure until a crack opens in the rock. Theories outrun the light because the light arrives late from the most secret theatres. The journey of photons is long, and the stage that produced them may have shifted in the interim. Mathematics travels faster, not in speed, but in reach, mapping the plausible terrains so that when a new glimmer arrives, a prepared mind can place it. This is not escape from experiment, it is escort. The escort stays close, adjusts course when the star finally becomes visible, and sometimes must turn back entirely. If reality keeps a final ledger of laws, it may be written in a script that appears alien and then obvious once learned. Many times before, concepts that seemed unnatural at first became the new plane sense. Curvature joined that path, and so did quanta. Another such turn may wait. Until then, the patience persists, the instruments breathe, and the equations continue to glow in the dark. At the turn of the 20th century, a furnace glowed inside a Berlin laboratory, while a quiet man counted energy as if it arrived in coins. Max Planck, seeking only a fit to stubborn data from blackbody radiation, proposed that light did not pour as a continuous syrup, but came in packets whose energy matched frequency, multiplied by a constant that now bears his name. The suggestion was cautious, even reluctant, yet it planted a seed that would alter every later sentence about nature. A world that had been smooth acquired a granulated whisper. A scale appeared where none had been expected. In a separate room of thought, a young patent clerk in Bern understood that these packets were not bookkeeping tricks. Albert Einstein saw in the photoelectric effect a physical event that demanded quanta with real teeth. The light released electrons from metal only when its frequency climbed past a threshold, and the pattern followed Planck's rule exactly. He then reshaped gravity into geometry, and gave mass and motion a stage that curved in response to energy. With the field equations, he turned the pull of apples and planets into the bending of space-time, a unity that carried an austere grace. The eclipse expedition led by Arthur Eddington traced the arc of starlight around the sun and pressed ink into the theory's passport. Curvature had left a signature in daylight. Meanwhile, a new grammar grew in the hands of Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. Atoms refused the steady orbits of planetary imagination. They jumped between fixed levels and hummed at precise frequencies. Heisenberg's matrices traded trajectories for relations between observable quantities. Schrödinger's waves filled space with possibility whose crest collapsed into fact. Dirac laced quantum rules to special relativity and found an equation that admitted a sibling for the electron with equal mass and opposite charge. When the positron appeared in cloud chambers, the mathematics had already set a place for it at the table. Probability became physical law, and certainty gave way to distributions that obeyed strict statistics. Two triumphs matured side by side and began to pull away from each other. Quantum field theory learned how to calculate with finesse. Richard Feynman's diagrams turned integrals into pictures, and pictures back into integrals with a musician's ease. Julian Schwinger and Sinetiro Tomonaga developed parallel formalisms that converged on the same astonishing precision. The anomalous magnetic moment of the electron could be computed and then measured to many digits, a feat that felt like listening to the universe whisper its own decimals. By the late 1960s and early 70s, a unified description of electromagnetic and weak forces took shape. Renormalized and predictively fertile, gravity resisted that same procedure, treating the gravitational field as another quantum field on a fixed background looked promising at first. Perturbative expansions could be written, gravitons could be drawn as lines on paper, and the familiar rituals could begin. Yet the infinities that arose would not be domesticated by the same counterterms that rescued quantum electrodynamics. The coupling of gravity carried dimensions that spoiled the program, and no finite list of corrections could rinse the integrals clean. Gerard Hooft and Martinus Veltman showed how to cure the electroweak theory. Pure gravity, examined order by order, refused to heal. Later calculations made the refusal explicit at 2 loops. The perturbative road ended at a cliff. The conceptual tension reached deeper than technique. Quantum theory presupposed an external time that beats like a metronome above all processes. General relativity made time part of the play, not the theatre. The geometry itself evolved, and the clock depended on the curve. Following this insight, Bryce DeWitt and John Wheeler wrote an equation for the wave function of the universe that set the Hamiltonian to 0. The result had the unsettling appearance of a cosmos without time. Dynamics hid inside correlations among observables. The problem of time stopped being poetry and became a concrete technical obstacle that any reconciliation would need to resolve. Black holes sharpened the issue into a paradox that anyone could state in plain words. Jacob Bekenstein argued that a horizon must carry entropy proportional to its area. Stephen Hawking then found that quantum fields in curved spacetime would make a black hole radiate thermally, with a temperature inversely related to its mass. A perfect absorber would shine like a stove. That light looked thermal, stripped of the details of what fell in. If it carried away energy without memory, a deep principle of quantum mechanics seemed to fail. If instead the information was somehow encoded in subtle correlations, the classical picture of horizons as point of no return required revision. The puzzle earned a clear title. Information had entered gravity's court. The larger story also gained a simple name. Quantum gravity no longer referred to a vague ambition, but to a crisp assignment. A single framework must one day explain how geometry behaves when quantum rules are unavoidable. Singularities predicted by classical equations in gravitational collapse, and in the earliest moments of expansion signaled domains where the current map ceases to be reliable. Penrose's theorem placed those singularities behind horizons under broad conditions. Cosmology found a similar boundary at the apparent beginning. Each warning pointed toward a regime that demanded both quanta and curvature at once. Institutions and instruments played their parts as the mystery settled into its mature outline. Colliders probed the standard model with increasing energy, while leaving gravity far beyond reach. Microwave telescopes traced faint anisotropies in the oldest light and suggested that the infant universe carried fluctuations that seeded all later structure. Laser interferometers read small strains in spacetime as waves from mergers arrived in quiet frequencies that no ear can hear. These achievements did not yet reveal quantum gravity, but they tightened the frame that any successful theory must fit. Personal temperaments also shaped the path. Einstein never warmed to the probabilistic heart of quantum mechanics, yet his critiques drew attention to the strangeness that later became the phenomenon of entanglement. Bohr defended the statistical core with a resolve that turned debates into landmarks. Wheeler encouraged a generation to think at once pictorially and rigorously, urging an exploration of foam at the Planck scale and bridges that formal solutions seemed to permit. Hawking's calculations and wry certainty gave the paradox its cultural outline. In lecture halls and corridors, the unsolved question moved like a weather system that speakers could not ignore. The vocabulary expanded, and the stakes became explicit. Background independence became a watchword for any program that wished to honor the central triumph of relativity. Renormalization dictated caution, showing that some interactions grow tame at high energies while others worsen, and gravity sat in the latter camp under naive treatment. Hints emerged that geometry might be statistical at root, that areas could be counted, that horizons might be thermodynamic surfaces. No single picture ruled, but the family resemblance among proposals suggested that information and structure belonged at the foundation. With the naming came a refinement of what would count as progress. A theory would need to recover ordinary general relativity at accessible scales, reproduce the confirmed successes of quantum field theory, and offer specific, in-principle, testable predictions that could be distinguished from alternatives. The task was not to imagine anything that combined the two, but to fashion a bridge strong enough for measurement to cross. Mathematicians joined with physicists to sharpen tools, from topology to operator algebras, to the geometry of spaces that fold and twist in ways a desk cannot display. Computer simulations became laboratories for worlds that could not be built. What began in a furnace spectrum and a photoelectric threshold evolved into a defined frontier. The packets that Planck counted, and the curvature that Einstein drew had met in problem sets, in paradoxes, in the behavior of horizons, and in the silence of singularities. The question now possessed a clear shape and a fluent name. Quantum gravity was no longer a slogan. It was a map without its central region. To step into that blank requires both the humility to let data lead when it arrives, and the nerve to develop mathematics that can welcome it. The century handed down the riddle along with the instruments for its eventual reading. The stage stands ready for the first trace of a signal from the regime where quanta and geometry finally converse without contradiction. A chalk line climbs and never stops, and the room grows quiet. On the board, the integral refuses to converge. The symbols amplify without restraint, and the sum that was supposed to describe a measurable effect instead erupts into a quantity that no instrument could register. Infinity arrives like a fire alarm. It is not a value, it is a verdict. In the heart of the most successful equations, something essential misfires when pushed to extremes. The shock is not that the universe is large. The shock is that the mathematics meant to capture it becomes meaningless at the very edges where guidance is needed most. Quantum fields introduce this jolt early. Every mode of a field carries a half quantum of energy, even in perfect vacuum. Add those 0-point energies across all modes, and the ledger explodes. The formal sum streaks toward infinity with unembarrassed speed. Renormalization enters as a craft born of necessity. One isolates the parts that can be absorbed into physical parameters, matches those parameters to experiment, and declares the remaining quantities predictive and finite. The method works with stunning precision for many interactions, yet the conceptual tremor persists. A theory that must be constantly trimmed by reference to observation hints at a deeper story, in which the trimmings become natural, not surgical. A second jolt comes from the way couplings change with scale. Renormalization is not just a broom that sweeps divergences into redefinitions. It is a microscope that reveals how forces grow tame or unruly as the energy of a probe rises. The renormalization group transforms a single theory into a flow across scales. The pattern is instructive and unsettling. Some interactions weaken at short distances, a grace known as asymptotic freedom. Others hide trouble far above laboratory reach. Quantum electrodynamics, for all its triumphs, suggests a distant energy where the effective charge would surge toward a singular blow-up known as a Landau pole. Few expect that pole to be real. New physics would intervene first. The very expectation is a confession that the luminous theory prized for accuracy is provisional. Gravity turns the jolt into a clang. Treat the gravitational field as a quantum field on a background, and the diagrams can be drawn. The series one hopes to tame with renormalization becomes an avalanche of counterterms. The dimensional character of the coupling guarantees that each new order brings unfamiliar infinities that cannot be swallowed by redefining a fixed set of parameters. The label non-renormalizable is less an insult than a diagnosis. It states that perturbative methods, so successful elsewhere, lack jurisdiction here. The shock deepens because the equations of classical gravitation are clean and geometric, while their naive quantization becomes a forest of unmanageable divergences. Two modes of success refuse to merge. Singularities in space-time complete the triad of disquiet. The curvature encoded by the metric can become unbounded. Tidal forces intensify without limit according to certain solutions. At a radius that glows with algebraic simplicity for a non-rotating, uncharged mass, the curvature grows wild as the center is approached. The technical expression is geodesic incompleteness. Some timelike and null curves end after a finite parameter, as if the universe terminated a journey that should have continued. Theorems compress this behavior into general statements. Under reasonable assumptions about matter and causality, gravitational collapse will produce a region where classical description fails. The singularity is not an object in space. It is the announcement that the language itself has fallen silent. A different infinity complicates the picture on the largest scales. Vacuum energy, conceived as the sum of 0-point contributions from fields, should curl spacetime with overwhelming strength. Observations instead point to a gentle, accelerated expansion, many orders of magnitude smaller than the naive estimate. The mismatch is so large that the word mismatch itself feels coy. One number seems to mock the other across a gulf that no known symmetry bridges. The cosmological constant problem stands like an obelisk, smooth on all sides, and far taller than the surrounding puzzles. It is difficult even to frame a satisfying partial answer. Cancelling immense contributions with equally immense but opposite ones is possible in equations. The taste it leaves is of fine-tuning rather than understanding. Fine-tuning arises again in the mass of the Higgs boson. Scalar masses are sensitive to high-energy details in a way that looks precarious when a cutoff is imagined. Corrections drag the mass toward the largest scales available. To keep the observed value light, a delicate conspiracy must be arranged among parameters. Naturalness. The principle that dimensionless numbers in fundamental laws should not require improbable cancellations, protests. The protest has animated decades of proposals for new symmetries and new particles that could soften the sensitivity. Experiments continue to delimit that landscape. The issue returns to the same heartbeat. The boundaries of a theory disclose how it will behave when pushed, and at those boundaries, infinity often stands guarding the next idea. Scalars in simpler settings provide a separate warning. A plane field with a quartic self-interaction in 4 spacetime dimensions risks becoming trivial in the limit where a cutoff is removed. If taken as exact, the theory offers no genuine interactions at arbitrarily small distances. The result is subtle and debated in detail. The lesson still carries weight. Some models that seem comfortable at everyday energies dissolve when asked to be complete in the ultraviolet. They must then be understood as effective descriptions, honest within a window and replaced beyond it. Singular behavior also invades cosmology near the beginning of expansion. Idealized models that extrapolate backward in time generate a moment when density and curvature diverge. The idea of a beginning is less a metaphysical claim and more a sign that the equations reach a boundary they cannot pass. Detailed analyses of early time dynamics reveal complex behaviors, with oscillations in anisotropic metrics and chaos-like patterns in the approach to extreme curvature. In that regime, the classical map appears to fray, and any credible account must reconcile quantum principles with geometry. The call for a more complete language is unambiguous and loud. Inflationary scenarios create their own need for careful thought. If tiny initial quantum fluctuations are stretched to cosmic scales, then modes present in the sky today originated from wavelengths that were once far below any known cutoff. This trans-Planckian concern does not refute the mechanism, but it asks for its embedding in a framework where such modes are described consistently. The inquiry is an echo of the larger theme. Success at accessible scales invites scrutiny of assumptions at inaccessible ones, where naive continuations can stumble into infinities or ambiguities. At this point, the role of infinity becomes diagnostic. It shows where extrapolation overreaches, and it hints that familiar degrees of freedom may not be the correct variables at ultra-short distances or ultra-large curvatures. The winsome picture is that different scales of nature host different languages, stitched together by flows and matching conditions. Effective field theory becomes not a compromise, but an organizing principle. Still, a final account would make such patchwork feel inevitable rather than improvised. The presence of uncontrolled divergences says the account remains incomplete. Instruments respond to these philosophical jolts with tangible strategies. Cutoffs are introduced, not as lies, but as declarations of scope. Counterterms are computed and fitted. Renormalization flows are mapped across many decades of energy. Lattice methods convert continuous fields into grids to allow non-perturbative study. Spacetime singularities are bracketed by horizons and examined through their thermodynamic avatars. None of these maneuvers hides the clear verdict written by the infinities themselves. They deny that extrapolation by habit is safe. They demand a revision of the ontology that underwrites the equations. Even language must adapt. Infinity in mathematics can be domesticated within convergent frameworks. Infinity in physics performs a different task. It bars entry and redirects traffic. Each divergent integral tellingly avoids specifying a numerically large but finite answer. It refuses arithmetic altogether. The refusal forces reconsideration of what is being counted. Perhaps degrees of freedom are not local in the naive way. Perhaps geometry itself is not fundamental but assembled from correlations that saturate before the blow-up. Perhaps dynamics is emergent from information bookkeeping that has its own saturation scale. These are sketches rather than claims. The key truth is simpler. Wherever infinity appears, a new conceptual variable waits to be named. Shock in the hard sense, has therefore become a method. By pressing equations until they fail, the path toward a deeper portrait of nature becomes visible as a silhouette. The list of divergences and singularities is not a catalogue of defeat. It is a map drawn with boundary signs. Finite measurements, already rescued by renormalization, and finite signals that skirt near horizons, testify that a consistent account exists within reach. The infinities shout where not to step, and whisper which new steps might be possible. A horizon bends light into a last, hesitant circle, and then the circle dissolves into darkness. At that boundary, the equations that govern motion begin to sound like thermodynamics. Temperature, entropy, free energy. These sober words from steam engines and ice melt slip into discussions of gravity as if they had always belonged there. The surprise is not merely the poetry of analogy, it is the accumulation of precise correspondences that behave like signals from the edge, a code that says information and area are married more tightly than intuition allows. The mechanics of black holes began as a curious mirror of ordinary heat. Surface gravity took the role of temperature. Mass took the role of internal energy. The area of the horizon behaved like entropy that refuses to decrease. These parallels were first noticed as formal relations that seemed numerology with good manners. Then a calculation made the mirror exact. Quantum fields placed on a curved background reveal that a hole emits a faint thermal glow, with a temperature set by its surface gravity and Planck's constant. The object once thought to be perfectly black becomes a body that radiates like a hot coal, although cold by everyday standards. The analogy clicks into identity, and the area that once was a geometric measure turns into a thermodynamic count. A thought experiment deepened the message. Imagine lowering a box of gas toward a horizon on a tether, letting gravity do work on the winch, then dropping the box when it hangs a breath above the boundary. If no entropy is assigned to the whole, the outside world could lose entropy without compensation, violating the second law. To prevent that offense, a price must be paid in the currency of area. The horizon must enlarge enough to balance the books. The proportionality that emerges is crisp. Entropy scales with area, not with volume. A bit landed on the surface raises the count by a fixed small amount, and the total tally is staggeringly large even for modest holes. A bound appears when this accounting is extended to any region. There is a maximum amount of information that can be crammed into a space of given size and energy, and that maximum scales like the area of the boundary measured in natural square units. The concept rescues the second law and offers a new intuition. Space is not an empty warehouse for endless records. It is a ledger with a finite number of lines, and the number of lines grows with the size of the boundary that encloses the records. The reversal from volume to area is not a small correction. It is a pivot in how storage is imagined by the universe. The same pivot shows up in the structure of quantum fields without gravity. Consider a region cut from space by an imaginary surface. The vacuum is not empty. It is a weave of correlations that tie the two sides of the cut. If one asks only about the degrees of freedom on one side and forgets the other, the forgetting produces entropy. That entanglement entropy diverges in a way that is governed by the area of the cut. The leading term is proportional to the surface, not the bulk. This is not a matter of radiation leaking from a star. It is the basic architecture of correlation in the ground state of the fields themselves. The appearance of area as the multiplier of uncertainty links ordinary quantum theory to the language that horizons forced upon gravity. Acceleration writes the same story in another key. A uniformly accelerated observer perceives the vacuum as a thermal bath with a temperature set by acceleration and fundamental constants. A horizon appears for that observer, a Rindler boundary that hides part of space. The warmth felt is the price of ignoring the hidden region. Once more, temperature is tethered to a horizon, and entropy arises from information that cannot be accessed. The message that reaches through these different situations is consistent. Boundaries create heat out of ignorance, and the measure of ignorance scales with area. Hints of microstructure accumulate. Certain families of black holes permit accounting of underlying quantum states with known tools. In select cases, the count matches the thermodynamic area law exactly, without adjustable parameters. Different approaches to quantum geometry produce spectra of area made from discrete quanta. When horizons are built from such quanta and then counted with careful combinatorics, the result recovers the same proportionality with a specific numerical coefficient once a single free parameter is fixed by comparison. The agreement across frameworks that otherwise disagree on many details feels like a repeated knock from the same door. Geometry itself reflects information in more direct ways, in models where a gravitational theory is paired with a quantum theory, living on a boundary at infinity. In that duality, the entropy of a region in the boundary theory is given by the area of a minimal surface in the interior that ends on the region's edge. The formula trades a measure of entanglement for a measure of geometry, as if correlation and shape were exchanging identities. Extensions of the rule allow surfaces that reach behind horizons to contribute to the entropy of radiation outside, suggesting that the very interior of a gravitational system can become part of the accounting that an external observer must keep. Boundaries in gauge theories introduce a practical complication that doubles as a clue. The constraints that ensure redundancy of descriptions must be satisfied on any cut-through space. To keep the rules consistent, extra degrees of freedom need to live on the cut. These edge modes restore the ability to factor the Hilbert space across a boundary and carry their own entropy. The count that emerges from these boundary degrees of freedom can be matched to the area law in gravitational settings, communicating the idea that a portion of the missing microstates might be stored on the surface itself in variables that only awaken when a boundary is declared. The horizon behaves like a physical system even if nothing crosses it. Pressures, viscosities, and conductivities can be assigned to a fictitious membrane that replaces the horizon in calculations for an outside observer. The membrane conducts currents and dissipates energy with specific coefficients. This portrait is an engineering caricature that reproduces many external behaviors of the exact solution, and it strengthens the intuition that something locally active resides at the brink. The surface is not a mathematical afterthought. It is a thermodynamic actor with responses that can be tabulated. Laboratories have chased echoes of this thermal behavior in controlled media. Sonic horizons arise when a flow exceeds the local speed of sound, and shallow channels produce ripples whose spectra carry the same thermal profile predicted for gravitational horizons. Condensed matter systems can mimic the kinematics of fields near a boundary, with enormous redshift and reveal soft quanta that frame a temperature. These are analogues, not astrophysical sources, yet they teach the mathematics to the hand and the eye. They show that the thermal character of horizons flows from causal structure and quantum fields, not from the detailed texture of astrophysical collapse. Astrophysical observations assemble their own quiet dossier. The late-time ringing of compact mergers is consistent with smooth horizons that love to absorb and then settle. No crisp echoes announce a hard surface where none should be. No dramatic deviations from the expected spectrum have been isolated in populations of accreting candidates. The discipline of measurement is cautious, and alternative compact objects with no horizons remain a topic of exploration. Yet the simplest reading is that nature builds horizons, and that those horizons behave like one-way membranes for classical fields, and like thermodynamic surfaces for quantum fields. The picture that emerges is not a single equation, but a mood imposed by many. Area is not an incidental geometric trait. It is a counter of microscopic possibilities. Temperature is not an optional flourish. It is a necessary cost of information hidden behind boundaries. Entanglement is not a parlor trick. It is the deep glue that knits the world into regions that know and do not know about one another. Horizons broadcast this lesson in a whisper the universe has made crisp enough to hear with mathematics, and in some cases with devices. The edge speaks of a cosmos that tabulates. It counts correlations across a surface and allocates entropy there, as if the world were storing its secrets on skins. That habit changes how explanations are sought. The correct variables may not be local fields everywhere. They may be patterns of relation that express themselves through area. The signal does not sketch the final answer, yet it fixes a direction. Information and geometry are partners. Where a boundary is drawn, a temperature appears. Where a cut is made, entropy rises in proportion to area. Space might not flow like water. It might count like beads on a wire, and the beads sit on the edge. Quantum theory keeps a strict ledger. Every isolated system evolves from a pure state to a pure state, with no erasure of microscopic detail. Gravity provides a stage where that promise can be tested with pitiless clarity. A massive star collapses, a horizon forms, and the object radiates with a temperature that depends on its size. The spectrum is almost perfectly thermal, indifferent to the stories of what fell inside. If the glow carries no imprint, the final state after complete evaporation is a mixed haze of heat. Pure to mixed without an external environment would contradict the ledger. The universe would appear to forget. The mechanism that creates the glow can be pictured as a duet. Quantum fields near the horizon jitter and briefly conjure paired excitations. One partner falls inward with negative energy relative to infinity, thinning the mass that feeds the fire. The other climbs out, adding to the outgoing bath. The two are entangled. To an observer who sees only the outside, the partner across the horizon has been traced out, which yields thermal statistics. The interaction respects locality at the scale of the horizon and uses no exotic ingredients. The paradox arrives not from a trick, but from the modest assumption that low curvature regions behave as usual, and that the horizon is a place of ordinary emptiness for a falling observer. Entropy tells the story in a single rising curve. Each emitted quantum increases the entanglement between the radiation and the remaining black hole. If evaporation ends in a final wisp of heat with no hidden residue, the radiation would remain entangled with nothing. The curve would climb until the last moment and then freeze at a large value. Unitarity demands a different picture. The curve should rise at first, reach a turning point at a time set by the initial entropy, and then fall as correlations leak back out. This ideal trajectory has a name used by many calculations. It is a path that begins with ignorance, peaks at a balanced trade between inside and outside, and ends with recovered memory. Conventional, semi-classical reasoning produces the monotonically rising line. The radiation is always new and always entangled with fresh modes that fall inward, so nothing outside can begin to purify what has already escaped. The conflict then becomes explicit. Either the smoothness of the horizon for infalling observers must be sacrificed, or the outward stream must carry long-range correlations that the semi-classical analysis misses, or the ordinary rules of quantum mechanics must fail. Each option is costly. Smoothness at the horizon is the gentle core of the equivalence principle. Hidden correlations in radiation must be delicate enough to evade simple calculations yet strong enough to purify a sea of nearly thermal quanta. Abandoning quantum rules breaks a structure whose predictions have rarely faltered. One proposal protects both unitarity and the peaceful horizon by appealing to a lesson in perspective. No observer can collect evidence for duplication of quantum information, so a single account may look inconsistent only if described from incompatible vantage points. An outside observer sees unitary evaporation. An infalling observer sees no drama at the horizon and no violation of quantum rules in the small neighborhood carried through the boundary. The apparent cloning never appears to any one laboratory. This idea ties consistency to the rights and limits of observers who cannot compare notes. It is a pragmatic piece, elegant in spirit, yet it invites sharper checks. A sharper check arrives from the exclusivity of quantum bonds. A late photon from the glow must be entangled with earlier radiation if the total state is to purify. That same photon, in the local picture near the horizon, was born in a pair that requires it to be entangled with its partner inside. A quantum cannot share maximal intimacy with two separate systems. If the bond to earlier radiation is real, The newly emitted mode cannot also be fully bonded to its partner across the horizon. The local duet is broken. The break replaces a gentle crossing with a wall of high-energy excitations that a falling observer would encounter. Smoothness yields to a furnace. The alternatives are stark. Keep the horizon calm and admit that information is lost. Keep unitarity and accept that the boundary becomes a place of violent disruption. Search for a different accounting, where the inside partner is not an independent degree of freedom a distant accountant can tally. The last option points toward an audacious possibility. The interior might be secretly encoded in the same degrees of freedom that the exterior radiation occupies. What appears to be a second copy is only a different decoding of a single set of qubits. The location of information is then not a simple matter of position in space, but of which code is being read. Clues about encoding come from the way complex systems mangle and hide inputs. Scrambling describes the rapid delocalization of information across many degrees of freedom. A black hole is an extreme scrambler, folding any incoming message into an almost featureless distribution on a short timescale. After that time, the next quanta that escape can in principle carry pieces of the message, though the recipe for recovery is extravagantly intricate. A patient entity with control over the entire radiation and a miraculous decoder could extract the imprint. There is no contradiction with practicality if the decoding requires resources that bloom like exponentials, or if the success hinges on delicate interference patterns that an ordinary laboratory cannot marshal. Chaos provides a diagnostic for this behavior. Certain out-of-time ordered correlations quantify how quickly an initial disturbance infects later observables. The fastest possible growth saturates a bound set by temperature and fundamental constants. Models that mimic black holes show this fastest growth, and the signature supports the picture of extreme scrambling. The message hidden in the glow is not absent, only folded into patterns that resist naive probes. The ledger of unitarity remains technically intact, even when every straightforward measurement insists on sameness. Geometry offers another set of tools to revisit the rising and falling entropy curve. In carefully defined settings, the entropy of radiation can be computed by searching for special surfaces that partition space and by allowing new geometric saddles to contribute when they reduce the cost. At early times, the minimal choice lies outside the horizon, and the computed entropy rises as expected. At later times, a configuration appears in which parts of the interior become included in the book kept by the radiation. The chosen surface jumps, and the count begins to fall. The full curve then follows the unitary path, without asking for a violent boundary or a failure of quantum law. The picture that follows from these calculations is subtle. The interior is not independent of the radiation when the global state is considered. A set of qubits outside can be organized through the logic of error correction to reconstruct specific operators that act as if they were located behind the horizon. The place becomes a property of the code. For practical observers with limited access and simple tools, the horizon still looks uneventful and the glow still looks thermal. For a hypothetical overseer with exacting control over enormous quantities of radiation, a different decoding reveals the needed correlations that restore purity. The paradox is softened by the distinction between what exists and what can be accessed within bounded effort. Thought experiments sharpen the lessons further. Toss a diary into an ancient black hole, wait the short scrambling time, then collect a moderate amount of additional radiation. If the evaporation is unitary, the content of the diary can be reflected out quickly, in principle, since the whole already shares large entanglement with its earlier glow. The system acts like a mirror that returns new inputs after only a brief delay. No law of physics is violated by this quick return, and the speed does not exceed causal limits. The difficulty lies in decoding and in the requirement to control a vast set of degrees of freedom with precision. The universe keeps its promise not to forget, while hiding the memory behind practical indifference. The stakes reach beyond astrophysical objects. If the world respects unitarity in the most extreme theatre available, then the lesson folds into every attempt to build a final account of space-time. Space may not own information in the naive way assigned by location. Ownership could be conditional on what algebra of observables a given agent can manipulate. Entanglement would then be not decoration but architecture, and the boundary between inside and outside would draw the map of what counts as real for a specific experimenter. What began as a paradox about heat becomes a referendum on memory. Either nature discards detail, or geometry disguises detail as inaccessibility, or the everyday picture of a placid horizon fails. The weight of evidence favours the view that the ledger remains balanced, that purity flows through a code too subtle for casual reading, and that any apparent loss is the shadow of an observer with limited reach. The glow that looks like forgetfulness is the light of a vault that will open only for a key carved from complexity. Imagine that the smallest ingredients of nature are not dots but threads. Each thread trembles with a set of allowed notes, and the music of those notes appears in laboratories as what are called particles. Replace the collision of points with the meeting of tiny loops or open strands, and a different kind of arithmetic takes hold. The smearing of interaction across a minuscule length softens the brutal spikes that plague point-like theories. Where a diagram once diverged, a surface now flows, and the ultraviolet tantrum calms. In that quieting of infinities sits the promise that gravity and quantum rules may speak a common language. The path of such a thread is not a line but a two-dimensional sheet traced through space-time. That sheet carries a symmetry that allows one to reshape its coordinates without changing physics, and at special values of space-time dimension, this symmetry becomes exact at the quantum level. In those dimensions, anomalies cancel with exquisite precision, a requirement that fixes the theory as much as it liberates it. One version, with only bosonic vibrations, prefers 26 dimensions and lacks the softness of fermions. When supersymmetry is woven into the sheet, the critical count lands at 10, and a tower of excitations organizes with balanced elegance. Among the vibrations of a closed loop sits a mode that behaves like a massless spin-2 particle. Its interactions at low energy reproduce the equations of curved geometry. In other words, gravity emerges not as an added feature, but as an unavoidable song of the loop itself. Open threads, by contrast, carry massless spin-1 modes that mimic gauge bosons, the carriers of forces familiar from particle physics. The pairing is natural. Closed strands wander the full expanse and whisper geometry. Open strands can anchor to hypersurfaces and conduct gauge dynamics along those embedded stages. Those hypersurfaces are dynamical objects in their own right. They accept endpoints of open strings, vibrate, carry tension, and stack to generate non-abelian gauge groups when many lie together. Intersections among them can localize chiral fermions, the handed matter that populates detectors. In this picture, the constituents of the standard model can live as notes on brains while gravity travels through the wider bulk. The separation explains why gravity appears so feeble at human scales. Its flux dilutes into dimensions that matter cannot access. A family of equivalences turns rigidity into resilience. A loop curled on a circle of radius r is indistinguishable from a loop on a circle of radius proportional to 1 over r, provided momentum and winding exchange roles. This duality trades large for small and announces a minimum meaningful length set by the tension of the string. As energy climbs, probing shorter distances ceases to reveal finer structure. Instead, the theory folds back on itself. A second duality relates strong coupling to weak coupling in companion formulations, suggesting that what looks intractable from one vantage is gentle from another. 5 superficially distinct, supersymmetric models, once thought to be competing claims, form facets of a single broader framework whose quiet extra dimension promotes membranes and 5 brains as fundamental actors alongside strings. The calculational machinery reflects these ideas in its grammar. Perturbation theory counts surfaces by their genus, a topological index that measures how many holes a sheet possesses. Each additional handle is weighed by a power of the coupling constant, so the expansion acquires a geometric clarity. Modular invariance, a symmetry that identifies deformed tori as equivalent, enforces finiteness of one loop amplitudes by gluing together regions of parameter space that would otherwise overcount extreme configurations. High energy scattering at fixed angles softens exponentially, another echo of extendedness. No point-like projectile can see structure finer than the intrinsic scale written in the tension. Temperature uncovers a different hallmark. The density of available excited states grows exponentially with energy, and the partition function reveals a limiting warmth beyond which ordinary heating ceases to make sense. This Hagedorn behavior suggests a new phase rather than a breakdown. At such temperatures, the intuition of strings melting into shorter strings fails. Instead, long strings proliferate and dominate, hinting at a statistical picture where length is traded against energy, like a currency with its own exchange rate. Geometry at human scales has far fewer dimensions than the critical ones demanded by consistency. The excess must curl tightly. Calabi-Yau manifolds, with their vanishing first Chern class and rich topology, serve as the silent rooms where extra directions hide. Their shapes decide spectra and couplings. Intersection numbers and harmonic forms translate into families of quarks and leptons, strengths of forces, and mixing angles. Mirror symmetry links pairs of such spaces in a way that swaps complex structure with Kähler data, turning intractable counts of curves into solvable algebraic problems. Mathematics and physics clasp hands in these correspondences, each confirming the other with unexpected accuracies. Vacuum selection is not automatic. Massless shape parameters roam unless anchored by background fields that thread cycles and pin sizes and angles. These fluxes warp the internal volume, lifting flat directions and generating potentials that can stabilize moduli. The mechanics is intricate and often supersymmetric to control quantum corrections. When the dust settles, a low-energy world can resemble the one measured by colliders, at least in principle. It remains a craft to choose constructions that preserve delicate features like small neutrino masses or the absence of rapid proton decay. Black holes become laboratories for counting when the setting is chosen with care. Configurations built from branes and strings, with charges and angular momenta arranged to preserve a fraction of supersymmetry, admit an exact enumeration of microstates, using index techniques that protect degeneracy against quantum deformations. The tally reproduces the area law, including its precise coefficient in regimes where classical geometry is trustworthy. Corrections can be computed and matched across descriptions. The success does not derive from a guess. It is a calculation that connects horizon area to an honest count of ways to assemble the object from fundamental ingredients. Scattering theory inherits surprising order from this framework. Relations appear that tie gravity amplitudes to the squared structure of gauge amplitudes. In some channels, the double copy is literal. A gravity integrand emerges by replacing color factors with kinematic ones in a gauge theory expression. While this insight can be framed without explicit strings, it was made natural by years of watching closed modes factorize into pairs of open modes on the worldsheet. Practical benefits follow. Loop calculations in gravity, once a forbidding thicket, become navigable when charted by gauge theory maps. Cosmology tempts with scenarios in which our visible expanse is a brane moving through a higher dimensional sea. Collisions of branes can seed bursts of energy that resemble early expansion. Inflaton candidates arise as distances between branes, with potential shaped by geometry and fluxes. Networks of cosmic strings could remain as fossils, their gentle gravitational pull tracing filaments across the sky, and their cusps releasing distinct bursts of waves. Such relics have evaded detection so far, yet the search teaches how to translate microphysical assumptions into macroscopic signatures. Critique keeps the vision honest. The characteristic scale sits far beyond direct reach, and many consistent internal spaces appear to host low-energy worlds. Predictive sharpness must be wrestled from this variety by finding principle, symmetry, or dynamical selection that narrows options. Still, the framework delivers unique strengths. Gravity is not appended, but derived. Ultraviolet behavior is organized by geometry and global symmetry on the sheet. Gauge interactions and chiral matter arise as natural excitations of extended objects. Dualities replace isolated models with a network that can be navigated from weak to strong regimes. A portrait coalesces in which vibration, surface, and symmetry take the places once occupied by particles, vertices, and brute force renormalization. The smallest tremors write spacetime as a melody. Brains compose the stages where forces perform. Dualities tune the instrument so different songs agree on their hidden key. Proof waits on a signature that the framework alone can predict and the universe alone can confirm. Yet even in the waiting, a discipline of ideas has formed. It gives gravity a microscopic accent, explains why short distances blur into softness, and shows how a single principle can house the entire known cast of fields. A map hangs in the mind that is too large to frame. Each point on it records a choice of hidden geometry, a selection of flux that threads unseen cycles, a value for couplings that decide how strongly particles speak to one another. The map is not a single world. It is an atlas of possible worlds. In that atlas, gravity and quantum fields can settle into many quiet arrangements. The idea is simple to state and heavy to carry. If many arrangements are allowed, which one does nature inhabit, and why this one rather than the others? Compact dimensions provide the first path into such plurality. Extra directions can curl into intricate shapes, whose sizes and angles must be fixed by fields that wrap their cavities. Each wrapping pins a parameter, and each combination generates a distinct vacuum with its own spectrum and interaction strengths. The variety swells quickly. What feels like a single theory outruns itself into a sea of low-energy possibilities, each internally consistent, each capable of harboring a cosmos. Landscape becomes the name for that immensity, a word that tries to domesticate a number that defies counting. Cosmic expansion proposes a way to explore the atlas. If the energy of empty space is high and repulsive, patches of the universe can inflate, decay through quantum events into lower energy states, and leave behind pockets where expansion slows and matter condenses. Elsewhere, the process continues, so the larger whole never finishes. Each decay can change the hidden geometry and the pattern of flux, so the pockets differ in their constants and particle content. The picture is sober in its mechanism and extravagant in its consequence. A multiverse assembled by tunneling and stability. Selection becomes the next unavoidable word. Not every pocket could shelter chemistry that persists, or stars that ignite slowly, or nuclei that do not shatter at the first touch. If the atlas contains all manner of settings, observers will only arise in the neighborhoods where conditions permit long stories to unfold. That simple observation turns into a rule of inference. Predictions must be weighted not only by dynamical likelihood, but also by the presence of structures capable of noticing the prediction. The principle is controversial in style and practical in effect. It converts sheer possibility into conditional expectation. One number concentrates this logic with austere power. If the energy of empty space is too large and positive, structure never congeals. If it is too large and negative, recollapse wins before complexity flowers. In a broad scan of vacua, values that permit galaxies are rare by ordinary counting, but common once the requirement of structure is imposed. The reasoning explains why an apparently unnatural smallness might be typical among observers who can ask about it. The argument does not prove inevitability, but it ties an otherwise puzzling constant to a statistical filter that any aware creature would share. Statistics in an infinite ensemble are treacherous. Eternal expansion appears to produce endlessly many pockets. Comparing endlessly many objects demands a measure, and different choices of what to cut and how to normalize can yield different answers to the same question. Probabilities lose their innocence. They remember the method by which they were computed. The measure problem takes a simple idea and exposes its technical marrow until a principle selects a unique regulator for the infinities. Predictions drawn from counts across the atlas keep a faint dependence on the lens used to do the counting. Self-location deepens the subtlety. An observer is a dataset with a specific history not a nameless point in a generic pocket. Any prediction drawn from the atlas must condition on the facts already in hand: the temperature of the background light, the observed abundances of elements, the distribution of galaxies in a given patch. All these narrow the plausible neighborhood. Laws are then inferred not for an abstract average across all observers, but for observers with these precise attributes. Typicality becomes a careful statement rather than a casual claim, and Bayesian updates replace universal declarations. Skepticism answers with a different project. Perhaps most candidate vacua are illusions when inspected for consistency with quantum gravity. Low-energy theories that look innocent may fail to admit a healthy ultraviolet completion. Distance in field space may imply towers of light states that spoil control. Forces may be bounded by relations that make gravity the weakest interaction in any consistent world. Such constraints draw a shoreline between inhabitable terrain and lethal swamps. If a firm shoreline can be charted, the atlas shrinks and predictivity grows. The hope is that consistency alone can prune the garden to a narrow path. Other selection principles try to bypass statistics. Dynamics can favor certain attractors, making some vacua far more reachable than others. The early universe may have drifted along valleys that focus evolution towards specific corners of the map. Even bolder ideas imagine reproduction through gravitational collapse, with parameters shifting slightly each time a new region buds, so that values that encourage star formation and black hole birth proliferate. None of these narratives is settled, yet each injects cause into choice, reducing reliance on environmental arguments that taste like resignation to some palates. Observation keeps a quiet scorecard. If pockets sometimes collided, the scars might linger as circular imprints in the ancient light with low contrast and large angular scale. A decay that left a slight negative spatial curvature could be read in precise distance measurements if the curvature were large enough. Early transitions might have released backgrounds of gravitational waves with characteristic spectra, now stretched and faint but not erased. Constants might vary in space if neighboring domains bled into each other through rare events. Searches for each signature exist, and each non-detection tightens what remains plausible. Prediction in this setting evolves into population inference. One constructs a distribution for a parameter across the atlas, applies the condition that observers arise only in narrow bands, weights by the abundance of pockets that satisfy the conditions, and asks what a randomly selected observer with those constraints should expect to measure. The program requires humility and bookkeeping. It is not a license to fit any number. It is a recipe that, if grounded by a robust count and a faithful measure, can yield narrow ranges for quantities that otherwise look arbitrary. In the absence of new symmetries, statistics can become a new kind of principle. The tension between breadth and explanation remains the soul of the topic. A single world with rigid laws feels like an ideal of science, crisp and austere. A multitude with varied laws feels like a capitulation, unless the multitude itself is compelled by an underlying unity. Dualities hint at such unity, relating descriptions that look different on the surface but share a deeper structure. Perhaps the atlas is the shadow of a higher simplicity, and the apparent choices are different faces of one inevitable framework. Or perhaps contingency is part of the final answer, and law and selection will share the stage without embarrassment. In the dark between data points, doubt is a responsible companion. An atlas without a compass cannot guide, while a compass without a map leads to repetitive circles. The practical task is to build both at once. Enumerate consistent vacua, tame infinities in the counts, refine measures that respect causal structure, and design observations that could reveal telltale scars or curvatures. At the same time, interrogate the shoreline where consistency fails, compress the space of options by principle, and hunt for hidden symmetries that collapse choices into necessities. The menu is long, the appetite finite, and the stakes nothing less than what it means to call a constant fundamental. Imagine space not as a smooth expanse, but as a lattice of relations. Each relation traces a loop, a path along which a test vector is transported and returned to its start, carrying a memory of the curvature it has encircled. Replace coordinates with these loop memories, and geometry becomes a record of parallel transport, compact and gauge-like. The continuum is no longer a stage that fields occupy. The continuum is an approximation to a deeper combinatorial weave. A classical reformulation makes this shift natural. Gravity can be cast in variables that resemble those of a non-abelian gauge theory, with a connection that plays the role of a field and a triad that carries the imprint of spatial frame. The connection is probed not by sampling its value at a point, but by tracing its holonomy along a curve. The basic objects are therefore loops and open paths, and the algebra they satisfy is determined by the group that rotates local frames. Geometry becomes a language of group elements and fluxes, compact and intrinsically finite. Quantum kinematics built from these ingredients is startlingly discrete. States are labeled by graphs embedded in space, the edges colored by spins that indicate how strongly the connection twists along that path, the nodes equipped with intertwiners that ensure local gauge balance. These spin networks are not decorative. They are the scaffolds from which space is assembled. Cut a surface through a network and count the edges it pierces, weighted by their spins, and an operator assigns an area with a spectrum that takes on isolated values. Volume operators act on nodes and return quanta that depend on the intertwining of incident edges. The eigenvalues are not continuous. They arrive as steps, separated by gaps set by a fundamental scale. A constant enters this story as a quiet dial. It does not alter classical predictions, yet it scales the discrete units of area and volume in the quantum theory. Choose its value, and the ladder of eigenvalues shifts accordingly. When the ladder is tuned to match the thermal accounting of horizons, the entropy aligns with the familiar proportionality between area and microstate count, a result that moves from heuristic to calculation when isolated boundary conditions are imposed. The same framework yields subleading corrections that fall with the logarithm of area, a delicate signature of combinatorics at the surface. Diffeomorphism invariance, the statement that smooth relabelings of points carry no physical content, finds a home naturally in this representation. Graphs that can be deformed into one another without cutting or regluing represent the same spatial geometry. Location loses its naive meaning. What matters is how edges meet, how spins flow, how nodes share intertwiners. Space becomes an equivalence class of networks, distinguishable only by combinatorial features. The insight is severe and freeing. Without a background metric, the theory speaks entirely in relational terms. Semiclassical behavior emerges when networks are large and their labels are high. States can be engineered whose coarse-grained areas and volumes reproduce a smooth metric to within small fluctuations. The quantum stitch is too fine to be seen by long wavelength probes. These weave states justify the trust placed in the discrete picture. They demonstrate how ordinary rulers and clocks can arise from an underlying lattice of group theoretic data. The art lies in constructing such states with enough flexibility to recover diverse classical geometries, and in showing that small disturbances propagate across them as expected. Dynamics introduces the most demanding questions. In canonical form, gravity carries constraints that express gauge redundancy and time reparametrization. Quantizing these constraints requires regularization procedures that respect background independence and maintain the delicate algebra among them. Ambiguities appear, each with physical consequences. One celebrated construction provides a Hamiltonian operator that acts by reshaping the graph locally, adding tiny loops that mimic curvature and updating volume quanta at nodes. The structure is compelling, yet extracting full predictions from it remains a long endeavor, with consistency checks, anomaly control, and semi-classical limits serving as guides. A covariant viewpoint describes evolution as a sum over histories of networks. Nodes sprout faces, edges sweep out ribbons, and a too complex grows that records how one spin network morphs into another. Simplicity constraints restrict labels so that the combinatorial structure reproduces geometric data of discrete polyhedra. In appropriate limits, amplitudes reduce toward those of classical discrete gravity, suggesting that the quantum sum knits towards smooth geometry when spins are large. The bridge between canonical generators and these covariant sums is delicate but increasingly navigable, turning kinematics into genuine processes. Black hole interiors form a separate testing ground for the granular picture. When symmetry reduces the degrees of freedom, the discrete evolution can be followed across the region where classical curvature explodes. Operators that measure volume refuse to vanish identically, and difference equations replace differential ones. The result is a bounce instead of a dead end, with geometry contracting to a minimal size determined by the quanta of area before re-expanding into a new regime. Time for a freely falling observer remains finite through this transition, a sign that the singularity has been softened by the underlying discreteness. Cosmology inherits the same mechanism. Homogeneous models quantized in the loop spirit show a deterministic evolution through high density. The scale factor does not shrink to zero. It reaches a smallest value set by the discrete spectra and then grows again. The energy density that triggers the reversal is finite, a universal threshold of order, the fundamental scale. This replacement of the classical divergence by a bounce invites careful contact with observation. Tiny imprints in the earliest modes of the background light, or in the statistics of primordial waves, have been proposed as witnesses of such a prehistory. The proposals are concrete, though difficult, and they motivate refined reconstructions of the earliest propagation of perturbations. Matter can be woven into the same fabric. Fermions travel along edges, meeting at nodes where intertwiners maintain gauge balances. Gauge fields thread holonomies of their own, nested inside the geometry that hosts them, and their fluxes are measured by operators constructed in parallel to those of gravity. Background independence remains intact, since all actors live on graphs. Renormalization is reimagined as coarse graining of networks, where blocks of edges and nodes merge into effective degrees of freedom. Group field theories treat the quanta of space as bosonic building blocks whose condensates might display continuum behavior, an approach that makes the emergence of large-scale geometry a problem in many body physics, rather than in classical limits alone. Phenomenology must tread with restraint. Discreteness tempts one to expect small violations of familiar symmetries, yet careful formulations maintain local Lorentz invariance where they must. Some scenarios predict deformations of dispersion at extreme energies, with light and particles feeling the weave in minute ways. Astrophysical observations already constrain such effects to be tiny, if present at all. The most robust windows remain thermodynamic counts for horizons, possible traces in early cosmological signals, and subtle correlations in high-precision measurements of gravitational phenomena where quantum fluctuations in geometry could, in principle, leave a fingerprint. The virtues and challenges of the framework are tightly paired. Background independence is a principled strength, eliminating the need to quantize on a fixed stage. Discrete spectra cure certain ultraviolet ailments by removing the very notion of arbitrarily small geometric quanta. At the same time, the absence of a background complicates comparison with the conventional perturbative tools that work so well elsewhere. Recovering the familiar graviton description, showing that the low energy limit reproduces the full suite of classical predictions, and anchoring dynamics in a form that is both anomaly, free, and unique, these remain the measures of success. Yet the imagery is powerful. An area is not a length stretched over a surface. It is a sum of contributions from strands that puncture a cut, each contribution labeled by a spin that measures a unit of twist. A volume is not a continuous filling. It is a tally of polyhedral cells where edges meet, their triple products knitting a lump of space. The whole of geometry is nothing but the organized matching of these local tallies, glued by gauge invariance and diffeomorphism symmetry into a shape that macroscopic eyes read as smooth and continuous. At small scales, space counts. At large scales, space flows. A theory that carves space into quanta invites a revision of intuition. Positions lose their privileged meaning, replaced by relations along graphs. Distances emerge from how many units of area and volume lie in the path of a measurement, rather than from real numbers assigned a priori. Curvature ceases to be a trait smeared over a region and becomes the residue of loops that refuse to close cleanly when parallel transport is performed. In that reimagined world, gravity is not a force. It is the bookkeeper of connectivity, the quiet sum over spins and intertwiners that tallies what space has chosen to be. Time is asked to speak, and it answers with events. Not a river, not a backdrop, but a quilt of transitions where something becomes slightly different from what it was. The granular image does not show seconds ticking. It shows moments knitting a fabric, each stitch a local move that reshapes adjacency. If space is assembled from relations, then time is the sequence in which relations are rearranged. The cadence is not imposed from outside. It is written by the order in which changes succeed one another. A history of geometry can be drawn as a foam. A foam is a two-dimensional complex where faces, edges, and vertices record how a network of spatial relations morphs. Faces remember how a strand of adjacency travels. Edges tell where three-dimensional chunks meet through evolution. Vertices mark elementary acts of change. Numbers live on these pieces, spins on faces that measure quanta of area, intertwiners on edges that tally quanta of volume, and amplitudes at vertices that weigh the likelihood of a specific local move. A state on a boundary is a graph with labels. A process in the bulk is a foam that spans between boundary graphs. The theory does not ask for an external clock. It assigns a weight to each consistent way of getting from one boundary to another. There is a quiet heritage behind this construction. A topological theory that knows how to assemble flat connections is taken as a starting point. Constraints then bend it toward genuine geometry. The constraints are called simplicity, not because they are easy, but because they force algebraic bivectors to arise from tetrads, turning an empty scaffolding into discrete pieces of metric data. Vertex amplitudes implement those constraints in the quantum sum. The resulting model preserves local gauge symmetry and reproduces, in the appropriate limit, the action for a piecewise flat spacetime built from glued polyhedra. Semiclassical behavior appears as oscillations of phase. For large labels, the weight of a foam concentrates near discrete geometries that extremize a discrete action. The phase is the classical action measured on that geometry, divided by Planck's constant, with signs chosen by orientation. Stationary phase then favors histories that solve discrete field equations, just as a path integral for a particle singles out near classical trajectories when actions are large compared to the quantum of action. In this way, a macroscopic notion of time, with its smooth durations and steady clocks, emerges from the constructive interference of many tiny updates. Local moves carry no global ticking. A vertex is not a tiny tick of absolute time. It is an atom of change, the minimal unit by which adjacency can be updated. When many such atoms line up in compatible ways, an effective parameter appears that human instruments call time. Different choices of parameters can label the same chain of changes. The choice depends on which internal degree of freedom is used as a clock. A scalar field that varies monotonically can serve. So can a function of areas or volumes that never reverses along the histories considered. Probabilities then become conditional. One asks for the chance that a geometric quantity has a certain value when the chosen clock reads a prescribed figure. This relational stance is not mere rhetoric. It rewrites what it means to predict. The central object is a transition amplitude between boundary data, not an evolution operator that advances an initial state through an external time. The amplitude encodes correlations among readings of many partial observables, each of which can play the role of a clock for the others. When a matter field is used as a clock, equations reduce to a Schrödinger-like form that marches the rest of the system with respect to that field. When no monotonic clock exists globally, the description remains fully covariant. and the order of moves is reinterpreted as precedence in the foam rather than absolute chronology. A complementary perspective ties flow to the state itself. Given a statistical state over observables, a canonical flow can be extracted that plays the role of time evolution. The generator is not an external Hamiltonian, but the modular operator of the state. The flow depends on the informational content of the system and on which algebra of measurements is available. In regions with horizons, this flow yields temperatures and time steps that agree with accelerations and gravitational potentials seen by local observers. Duration becomes a property emergent from knowledge and restriction, not an ingredient specified at the outset. Coarse graining turns many small foams into a few large ones. Just as a fluid can be described without tracking each molecule, a network of microscopic moves can be summarized by effective transitions among larger chunks. The renormalization group becomes a flow on the space of amplitudes assigned to elementary building blocks. Fixed points of that flow mark universality classes where details of microstructure wash out. The task is technical and conceptual, requiring control over combinatorial sums and careful treatment of gauge redundancies. Progress has arrived through tensor network methods and group field theories that recast quanta of space as excitations of a field defined on a group manifold. Condensates of those quanta can behave like homogeneous geometries, and fluctuations above them like perturbations that travel as gravitons. Another disciplined route to granular time constructs geometry from triangulations that obey a causality rule. Only those assemblies are summed that admit a consistent slicing into spatial hypersurfaces, ordered by a time label whose meaning is purely combinatorial. The sum is Lorentzian, not Euclidean. The causal restriction stabilizes the ensemble, preventing the geometry from foaming into pathological crumples. When volumes are large, a four-dimensional effective spacetime emerges, with a shape that resembles a maximally symmetric solution with positive curvature. At very short scales, the spectral dimension, a measure of how diffusion explores the fabric, flows toward 2. This running suggests that the microscopic weave offers fewer directions to a random walker than the macroscopic one does. Short distances feel lower dimensional than long ones. Granularity need not violate cherished symmetries. A discrete foundation can preserve local Lorentz invariance in averages that matter for observations. The granules are not cells laid on a fixed grid. They are quanta that transform appropriately under changes of frame and that arrange themselves without selecting a preferred rest. Apparent violations can be made arbitrarily small if the sum over histories respects the full set of symmetries in the way combinatorics permits. The lesson is precise. Discreteness is not necessarily a lattice in the pedestrian sense. It can be an algebraic discreteness that speaks the language of covariant geometry. Observables reflect the process character of the picture. A quantity becomes meaningful when it sits on a boundary that isolates a process. The amplitude is then a function of that boundary data. This boundary framework resembles scattering theory, with initial and final states replaced by general boundary states defined on closed or open spatial surfaces. Measurements are then assignments of geometric and matter labels on those surfaces. Probabilities are extracted by squaring amplitudes in a way that respects gauge relations. The world is sliced into regions without assuming a global timeline, and each slice is treated as an experiment whose outcome is a set of boundary readings. Clocks themselves become physical systems subject to quantum limits. No perfect clock exists. Any device that tracks change carries energy and fluctuates. These fluctuations undermine the sharpness of temporal predictions when pushed far enough. The fundamental blurring appears as an unavoidable spread in correlating one observable with another used as a clock. The effect is deep rather than large. For everyday durations, the blurring is invisible, but for extreme accuracies, the idea that time is exactly known loses grounding. The arrow of time then aligns with growth of entanglement and with the statistics of coarse graining. The direction in which correlations become less special is the direction called future. Signals for such granularity will be subtle. A faint energy dependence in travel times across astronomical distances, a tiny distortion in the distribution of primordial gravitational waves, a residue of combinatorial order in the noise of precise interferometers. Each has been contemplated. Constraints already push many naive expectations to minuscule levels. Still, the program instructs how to translate structural assumptions into numbers. It teaches where the foam would leave fingerprints if it interacts with fields in simple ways, and how to hide if the sum over histories conspires to keep macroscopic symmetries exact. A coherent moral accumulates. Time is not laid on top of the world. It is the bookkeeping of change, extracted either from internal degrees of freedom that can serve as clocks, or from the state of knowledge that tells an observer how to flow. Histories are not curves drawn in a pre-existing stage. They are weighted assemblies of elementary updates, each update a small reweaving of adjacency. Continuum duration is the emergent smoothness of many consistent moves, much as temperature is the smoothness of many collisions. The granules are neither ticks of a cosmic metronome nor grains in a rigid hourglass. They are the minimal acts by which geometry remembers that something happened. Imagine a distant screen that never dims, a boundary encircling a world like a taut drumhead. On this screen, patterns flicker, phases rotate, correlations braid and unbraid. From only those boundary motions, a full interior appears to take breath. Mountains curve, stars orbit, horizons form, and a traveller could fall for a lifetime before touching a singular glow. The suggestion is audacious and simple at once. The information needed to specify a volume may live entirely on its rim, and gravity inside may be nothing more or less than the accounting rules engraved on that rim. A precise stage gives this idea its sharpest voice. Picture a space-time whose edges are infinitely far yet visible, where light launched from the interior can, given enough time, brush the boundary and return. Along that boundary resides a quantum field theory without gravity, a many-body system with symmetries that match the geometry of the enclosing rim. The claim is an equality rather than an analogy. Every bulk process has a partner in the boundary theory, and every boundary correlation has a geometric echo in the interior. Particles in the bulk correspond to operators on the edge. A black hole in the bulk is a hot state on the edge. The dictionary is exact, even when translation is hard. Coordinates in this dictionary reverse familiar intuitions. Short distances on the boundary interrogate regions near the outermost layers of the bulk, while long distances on the boundary see deep inside. Ultraviolet on the screen maps to near-boundary structure in the interior. Infrared on the screen maps to the throat where gravity is strongest. This exchange is not a slogan, but a working guide to calculations. Renormalization on the boundary becomes radial flow in the bulk. By climbing from long wavelengths to short on the screen, one walks outward in the interior, toward the place where the geometry touches infinity. Thermal behavior becomes geometry with a suddenness that feels like revelation. Heat on the boundary is captured by a horizon in the interior. Temperature is surface gravity measured by a geometric clock. Entropy becomes the area of a slice that wraps the horizon. The same conversion reaches into quantum correlations. If one divides the boundary into two regions and asks how much the first is entangled with the second, the leading contribution is the area of a minimal surface in the bulk that ends along the dividing curve. Static cases choose minimal surfaces. Time-dependent cases choose extremal ones. But the principle holds. Entanglement on the edge is length or area inside, measured in natural units. Geometry is cloth woven by quantum links. Locality, often taken as the non-negotiable foundation of spacetime, shows up as a property that the code on the boundary can approximate and protect. Operators that act on small bulk regions can be reconstructed from many different boundary patches, provided the patches are large enough and appropriately placed. This redundancy is the signature of an error-correcting code. The bulk is the logical subspace protected by the Hilbert space of the boundary. Erase a boundary region smaller than a certain threshold, and bulk data remain recoverable from what is left. Erase too much, and recovery fails. The threshold matches the geometric domain that a boundary region controls inside. a domain now called its entanglement wedge. Place a bulk operator inside that wedge, and some boundary representation exists that reproduces its action. Move it outside, and the representation disappears. Toy models make the logic visible. In discretized networks built from perfect tensors, a set of boundary legs encodes bulk legs with redundancy. Minimal cuts through the network count entanglement, and geodesic lengths become sums across strands. The tiling resembles a negatively curved space, and the layering of tensors mirrors the layering of renormalization. While such networks are coarse cartoons, they teach a lesson that survives refinement. Entanglement is not a garnish on geometry. Entanglement is the loom that weaves geometry, with bond dimensions standing in for cross-sections and minimal cuts standing in for extremal surfaces. Another translation of the same rule speaks in flows rather than cuts. Imagine incompressible streams that run through the bulk, constrained never to exceed a fixed density anywhere. The maximum total flux from one boundary region to its complement equals the entanglement between them. Where the flow saturates, the interior surface that chokes it matches the minimal surface of the earlier prescription. In this view, information is a fluid with a speed limit, and the shape of space is the shape that channels it. The theorem that proves the equality is technical. The picture it leaves behind is tactile. Dynamics respects the same ledger. Bulk fields satisfy equations of motion that can be solved by smearing boundary operators with kernels that reach inward. The reconstruction is subtle. Only combinations that are causally allowed appear, and ambiguities reflect the right to choose gauge and the limits of any boundary patch. Yet the result is general. Insert a disturbance on the boundary, and a wave moves inside along the light cones of the bulk theory. Change the state on the boundary, and the interior geometry shifts to match, sometimes gently, sometimes catastrophically, depending on energy and pressure. Gravity responds to stress as coded by the field theory, and the code respects causal order. Beyond clean geometries that curve like saddles, the principle searches for new stages. Flat space at infinity suggests a screen of another sort, where the algebra of asymptotic symmetries becomes the scaffold for a boundary theory of angles and energies carried away by light. Expanding universes tempt with rims that are not spatial infinity but cosmic horizons, where observers can see only a patch and must infer the rest from the way statistics change when edges move. None of these extensions yet enjoys the clarity of the original equality, yet each is a laboratory for the same instinct. When gravity organizes the interior, a non-gravitational ledger on a boundary may store the complete account. Concrete use has followed the poetry. Strongly coupled fluids on the boundary flow with viscosities that translate into universal ratios in the bulk. Impurities and lattices in a boundary material create pinning and transport phenomena that the interior renders as geometry with broken symmetries. Phase transitions on the edge become topology changes inside. Spectral gaps, Fermi surfaces, superconducting domes, strange metals with linear resistivity all admit geometric avatars that compute difficult boundary observables with ease. The flow of energy, the decay of currents, and the scrambling of information become geodesics and horizons and quasi-normal ringing. While the match is often qualitative and sometimes permissive, the calculational power has reshaped how strongly coupled systems are imagined. Complexity adds a final speculative hour hand to this clock. Prepare a pure state on the boundary and let it evolve. Its entanglement entropy saturates at a value set by the size of the region. Yet some geometric quantities continue to grow for far longer, such as volumes of particular interior slices or actions computed on carefully defined domains. The suspicion is that these quantities track the minimal number of simple gates needed to reach the evolving boundary state from a reference, a count of how hard it would be to build the state by elementary steps. If correct, then the interior continues to lengthen as computation deepens, long after entanglement has equilibrated. Depth, not just spread, would be a geometric attribute. The thought that a world can be encoded on its boundary invites a shift in philosophical posture. Space and mass and light would not be lost in the translation, only rewritten. A planet would be a phrase on the screen, but a phrase whose grammar compels the same orbits and the same tides. A horizon would be a hot sentence. A collision would be a burst of punctuation that briefly overwhelms the page before settling into new syntax. The boundary is not a metaphorical theatre. It is a lawful alternative description that refuses to waste symbols. If the interior appears extravagant, the screen explains the extravagance as economical bookkeeping. Nothing in this picture negates the reality of depth felt by instruments. Depth is the convenience of a dual language that makes locality manifest. The screen, in turn, makes unitarity and quantum statistics manifest while treating gravity as a derived emergent. The two together form a braid strong enough to lift problems that resisted either alone. Whether the cosmos has actually lived sits perfectly within such an equality is a question that waits on fresh insight. Yet the method has already taught a durable lesson. Information writes geometry. Boundaries remember more than edges should. And sometimes a page, if written with the right alphabet, contains a world. Two detectors blink on opposite shores of a dark sea. Their readouts stutter in unison, a quiet rhythm of correlated clicks, and the correlation survives separation. No signal has crossed the gap, no messenger has braved the space between, yet the pattern persists. Entanglement is the name given to that stubborn companionship. Geometry offers a different name, one that belongs to the language of curvature. It calls the companionship a bridge. A bridge in gravity takes a specific form. Solve the equations for a compact object, and under certain choices of mass and charge, a second exterior can appear, glued to the first through a throat. The passage is smooth in the mathematics and hopeless in practice. Any traveller who tries to cross will be crushed by tides or trapped by a horizon that refuses release. The bridge is there in the solution, yet it is not a tunnel for traffic. It is a relation between two regions, a relation that cannot be used to communicate. Entanglement feels similar. Two systems are prepared together in a pure state that does not factor. Measurements on one reveal patterns in the other. No matter the distance, yet nothing useful can be sent faster than light. The companionship neither carries a signal nor breaks causality. It is a relation that sits beneath messages, not a message itself. The parallel is not yet a theorem, yet it invites a daring identification. Perhaps a pair of entangled systems is, under the skin of a dual description, connected by a geometric throat. The throat does not permit travel, just as entanglement does not permit signaling. It is a map from correlation to shape. A sharp playground makes the identification crisp. Imagine a hot object in gravity that radiates as anybody would, yet also admits a cold description on a distant screen, where a quantum theory of many degrees of freedom holds all of its microstate information. Prepare two copies of the screen theory in a special joint state that correlates every mode in one with a partner in the other. In the language of gravity, the state describes two black holes that share a smooth interior. The pair forms a two-sided geometry joined by a throat. Neither side alone contains a complete description of what lies behind the horizons, yet the pair together carries enough data to draw the bridge. The shape of the throat stores information about entanglement. Increased correlation between subregions on the screens and the minimal surfaces that measure their mutual information stretch deeper into the interior. Reduce correlation and the surfaces retreat. In the limit of no shared entanglement, the throat pinches. Space-time hides behind statistics. Geometry becomes a portrait of how strongly parts of a quantum state are knotted together. A paradox then tempts the impatient mind. If a bridge connects the two exteriors, could a message be threaded through the throat? Classical energy conditions answer no. Any attempt to hold a passage open encounters a rule that focuses light rays and chokes the channel. The conditions are not arbitrary. They are statements that energy densities measured by physical observers are non-negative under ordinary circumstances. The rules kill hope, and by killing hope, they preserve causality. Quantum matter bends the rules. Fluctuations can produce patches where the local energy density dips below zero for a time and over a region that obey strict inequalities. The effect is small and regulated, yet real. With the right arrangement, a gentle negative energy pulse can flow along the throat and relax the focusing that blocks passage. The pulse does not create a grand doorway. It trims a narrow corridor that stays open for an instant. On the screen side, the same operation appears as a deliberate coupling between the two copies, an interaction turned on briefly and then switched off. The coupling lifts a tiny piece of entanglement and places it into a channel that a specific excitation can use. A messenger can now ride the corridor, provided the messenger is prepared with exquisite timing and modest energy. Too much energy collapses the passage. Too little misses the window. The arrival is not guaranteed, but the probability becomes non-zero. No rule of relativity is violated. The negative energy is arranged by a local laboratory at one screen, and crucially, the coupling that created it is a classical instruction that may require coordination between the screens. The messenger still depends on ordinary communication to set the stage. Faster than light signaling remains impossible. The recipe for sending a message through the bridge bears a familiar outline. In ordinary teleportation, two parties share entanglement. One performs a joint measurement on a local system and on her share of the pair, then sends a classical string that instructs the other how to reconstruct the state on his side. The state does not fly, the information does, and the reconstruction uses the pre-existing entanglement as a resource. In the gravitational retelling, the joint operation is the brief coupling between screens. The classical string is embedded in when and how strongly the coupling is applied. The reconstruction is the particle that emerges from the far mouth of the throat. Teleportation acquires a literal journey. The interior becomes the path by which entanglement and instruction produce arrival. Scrambling sets the earliest time when this stunt can work. Any message tossed into a hot object is pulled into turbulence that smears its details across the most microscopic degrees of freedom. The delay before the details become thoroughly hidden sets a scale. Only after that delay does coupling the screens allow retrieval on the far side. The delay depends logarithmically on the entropy, a sign of extreme efficiency. Nature hides information quickly. The bridge length mirrors this hiding. Immediately after formation, the throat is short. As time passes, the interior stretches. The same growth appears in a distinct language, as the rising difficulty of preparing the evolving screen state from a simple reference. Complexity becomes a clock for depth. Chaos measures the fragility of phase relationships that carry messages. If the two screens sit in a state that saturates the maximum rate at which small changes infect later observables, then a simple kick at one end becomes a turbulent pattern by the time a rescue attempt is made. The negative energy corridor must be arranged with care, tuned to match when the turbulence will carry the ferry to the mouth. That tuning shows up as a delicate phase in the coupling and as the need to act before the throat lengthens beyond retrieval. The picture lifts to thought experiments with diaries and mirrors. Toss a diary into one black hole and wait for the short time it takes to scramble. Then apply the special coupling. Moments later, a partner can read the diary as it emerges from the other side. No contradiction infects the procedure. The coupling carries the classical instruction needed to reconstruct the content. An observer who skims the surface without coordinating the intervention sees nothing but nearly thermal light. The miracle appears only to those who arranged the feat in advance. Laboratories far from astrophysical drama have started to build small analogues. Systems of many interacting spins or fermions can be engineered to exhibit strong chaos and heavy entanglement. Couplings can be turned on with control that would be impossible near a true horizon. Correlators that diagnose teleportation through an effective channel can be measured. The geometry is indirect, yet the logic is the same. The ability to route a signal depends on shared entanglement, on carefully timed interactions, and on a pattern of correlations that mimics a throat. All these constructions protect causality by a single habit. Entanglement builds bridges, yet a bridge cannot be used until an additional step creates a usable door. That step relies on operations that cannot spread influence outside the light cone without help. The classical instruction keeps time safe. The quantum resource that makes passage possible cannot be created by local action alone. It must already be present, and its presence cannot be arranged by messages that travel faster than light. Speculation follows with restraint. If correlation maps to shape, then changing correlation changes shape. Learning how to sculpt entanglement could become a method to design interiors with desired properties, at least in controlled models. The proposal is not engineering in space. It is engineering of states that draw the spaces in the dual description. The approach turns geometry into a technology of information. The materials are qubits and couplings. The blueprints are patterns of correlation. The finished object is a throat whose length, width, and openness correspond to entanglement, complexity, and the spectrum of allowed operations. A quiet thought lingers. Companionship between particles is not sentimental. It is structure. The structure refuses to localize, and when translated through the right dictionary, the refusal becomes a bridge. Two regions once isolated become one connected room in the deeper description. Signals still respect light. Causality still keeps its watch. Yet correlation writes new corridors into the architecture. Space in that view is a consequence, and bonds that began in probability become tunnels that guide falling stones and emerging messengers. The bridge is not fantasy. It is the shadow that entanglement casts into geometry. A whisper of order can carry the weight of a world. Imagine a list of events, each tagged only by which ones can influence which, a partial order, with no rulers and no clocks. Nothing else is given. No distances, no angles, no coordinates. Only the rule that cause precedes effect. From that sparse instruction, a skeleton of space-time begins to rise. The blueprint is austere. Take a set of elementary events. Impose transitivity so that if one can influence a second and the second a third, then the first can influence the third. Forbid loops so nothing can cause itself. Demand local finiteness so that any two events bound only a finite number of events between them. With those three clauses, the set becomes a causal set, a posset trimmed for physics. Volume is then nothing but number. Count the events in a region, and the count plays the role of volume in the continuum it approximates. Embedding such a set into a smooth geometry asks for a faithful map. Randomly sprinkle points into a Lorentzian manifold by a Poisson process, so that the expected count in any region equals its spacetime volume in fundamental units. Order the points by the manifold's causal relation. The result is a causal set distributed without a preferred frame, because the Poisson sprinkling respects Lorentz symmetry in its statistics. If two manifolds generate the same causal set, with high probability when sprinkled finely, they must be nearly the same in their causal structure and volume measure. The conjecture is bold in name and intent. The causal set would then fix the manifold up to small ambiguities, and the partial order with counting would be the whole metric in disguise. Geometry reappears as statistics of order. Proper time between two events is encoded in the length of the longest chain that links them. Dimension is revealed by how the population of order intervals scales with the size of those intervals. Curvature can be inferred by carefully weighted counts of small structures that involve a few relations. These recipes carry technical names, but their spirit is plain. Replace lengths and curvatures by tallies of precedence patterns, and the tallies converge to the continuum quantities when the sprinkling is dense. Where the continuum breaks down, the tallies keep their composure. Dynamics asks for a rule that grows the set without breaking the democratic spirit of label invariance. In a classical scheme, the causal set accretes one element at a time, each new event choosing its ancestors according to probabilities that depend only on the order, not on any hidden labels. Discrete general covariance is the watchword. The probability of any growth history depends only on the final unlabeled poset, never on the order in which elements were added along the way. A principle of Bell causality trims how probabilities can relate when new births have disjoint pasts. These conditions narrow the allowed growth laws to families that can be written down and studied. The set then becomes a history of births, a causally respectable genealogy. Quantum dynamics replaces probabilities with a generalized measure on histories. Amplitudes are assigned to causal sets rather than to trajectories on a background. Interference among entire orders takes the place of interference among paths. The framework is deliberately minimalist. It abandons wave functions on a fixed time slice and embraces a decoherence functional that weighs whole stories. Defining a workable quantum measure that leads toward a continuum limit and reproduces Einstein's equations in an appropriate regime is an open craft, but the scaffolding exists. Quantum mechanics is recast as a theory of which histories can coexist without contradiction when coarse-grained. Matter fields can be taught to live on the order. A scalar field becomes a function from events to numbers. The retarded wave operator is built from non-local sums over the first few layers of the past of each point, with coefficients chosen so that the discrete expression converges to the continuum d'Alembertian when the sprinkling is dense. The non-locality is gentle, controlled by a scale that lies only a few spacings above the fundamental grain. Lorentz symmetry is preserved in the mean because the sums average over invariant causal pasts. Green functions, propagators, and even a prescription for a vacuum arise from this retarded architecture. The ground state becomes the least bias solution compatible with causality in the order rather than with mode decomposition in a coordinate frame. Curvature enters through an action that counts order intervals with precise weights. The recipe samples a finite number of layers within each light cone and subtracts combinations that cancel lower order contributions, leaving a term that converges to the scalar curvature integrated over volume. Variation of this discrete action with respect to the order is subtle, yet the program is clear. Replace the integral of curvature by a sum over small relational motifs. Replace functional variation by comparison of nearby growth laws. Seek fixed points in which large causal sets behave like classical solutions, while fluctuations encode quantum geometry. Discreteness that respects Lorentz symmetry invites new phenomenology. A world line sampling the set could undergo tiny, frame-independent swerves in momentum space, a diffusion so weak that ordinary tests feel nothing but persistent enough to shift distributions over astronomic times. Photons could retain exactly luminal propagation, while still experiencing minute fluctuations in phase that widen interference patterns only beyond extravagant baselines. These hints are modest. They serve as reminders that discreteness and symmetry can coexist without coarse scars, making experimental signatures delicate and highly constrained. Cosmology offers a different angle. If the total number of elements in a cosmological region sets an effective ultraviolet and infrared balance, fluctuations in that count feed a fluctuating vacuum pressure. The variation would scale like the inverse square root of the number of elements, automatically tiny in a vast universe yet non-zero. The sign would meander in time, tilting expansion slightly above or below the mean. Such a stochastic pressure would resemble a small, persistent, ever-present component that neither dilutes away nor overwhelms structure. Observation corrals this idea into narrow corridors, but the conceptual payoff is striking. A constant that vexes the continuum becomes a fluctuating statistic in a granular ledger. Entropy has a new interpreter when order rules. Hilbert spaces do not factor cleanly across a sharp boundary in a relativistic quantum field because of constraints that glue the two sides. In an order-based world, the natural partition is a causal cut, the set of events that can influence one side but not the other. Entanglement then becomes a count of correlations across that cut, regulated by the non-local thickness that the discrete wave operator requires. The leading term scales with the size of the interface measured by how many links cross it, suggesting an area law born from the combinatorics of precedence rather than from ultraviolet modes that live on a fixed geometry. The recovery of the continuum sits at the center of all of this. Random sprinkling ensures no frame is favored. Counting ensures volume is honest. Order ensures light cones and causal diamonds appear as they should. From those three pillars, distances can be reconstructed, dimensions estimated, and curvature inferred. The emergent manifold does not have to be postulated. It is reverse engineered from the statistics of a deep partial order. Objections teach as much as successes. Without coordinates, comparing with the sharp predictions of graviton scattering is difficult. Without a canonical time, importing Hamiltonian intuition is awkward. Without an agreed quantum measure on sets, extracting robust predictions needs fresh tools. Each difficulty is also a test of the central claim. If causal precedence truly stores all the geometry the world needs, then coordinate-dependent observables must give way to order-based ones, and the calculational habits of continuum fields must evolve toward new combinatorial grammars. The philosophy stays spare. Events are fundamental. Order is law, number is volume. Geometry is a statistical echo. Gravity is the dynamics of order constrained by a principle that hides labels. The elegance lies in how little is assumed. No background is required, no lattice is drawn, no global clock is declared. A skeleton of arrows between events stands in for the richest geometry known, and when the arrows are many and well ordered, smoothness grows over the lattice of precedence like moss over stone. From such a sparse alphabet, a sweeping script is written. Light cones arise as the outline of what can be influenced. Time-like curves are chains that cannot be extended. Areas and volumes are counts of relations that straddle cuts and fill diamonds. Curvature is a slight bias in how many patterns are found compared to an uncurved benchmark. The world that instruments infer is not denied. It is decoded. Space-time is a story told by causal order, and the grammar is the partial order that every laboratory already respects. A drum is struck, and the room answers with pitch and overtone. By listening long enough, one can begin to guess the drum's shape. Geometry, in that mood, is not a drawing, but a spectrum. The distances and curves of a space are encoded in the frequencies of an operator that lives on it. From this thought grows a radical suggestion. Coordinates need not be numbers that commute. They can be operators whose order matters. Where ordinary maps multiply functions point by point, the new map multiplies them with a twist. Space becomes an algebra. Curvature becomes a songbook of eigenvalues. The bridge from pictures to algebra is precise. A smooth space can be recovered from the algebra of all continuous functions on it. Every point is a character on that algebra. Every distance can be read from how functions vary. Replace the commutative algebra by a non-commutative one, and the notion of point dissolves. Yet the tools of geometry can be rebuilt without points. The replacement is a triple of data: an algebra that plays the role of functions, a Hilbert space that holds spinors on which the algebra acts, a Dirac operator that differentiates by taking commutators. The operator is the inverse of a line element in this language. Its spectrum is the music by which shape is recognized. Distance acquires an unexpected definition that no longer asks for curves. Between two states on the algebra, the distance is the supremum of how differently they evaluate functions whose commutator with the Dirac operator stays bounded by 1. The inequality is technical, but the picture is simple. Only those functions that vary gently with respect to the Dirac operator may probe separation. The largest difference they can register is the distance. When the algebra is ordinary functions, the formula collapses to the usual metric. When the algebra fails to commute, an honest length persists even without points. Differential forms reappear as commutators with the Dirac operator. Gauge fields arise as inner fluctuations of the operator itself. Conjugate the Dirac operator by unitary elements in the algebra, and a connection term is generated. The curvature is the commutator of covariant steps. Integration is replaced by a trace that counts large eigenvalues of the operator, averaged in a specific way. With these ingredients, one writes an action that depends only on the spectrum above a cutoff. In an asymptotic expansion, familiar terms return. The Einstein-Hilbert action for gravity, kinetic terms for gauge fields, potentials for scalar fields, all appear as coefficients in a spectral sum. A tiny internal space illustrates the method vividly. Take a product geometry formed from a smooth four-dimensional manifold and a finite non-commutative algebra that is the matrix shadow of a handful of discrete points. The algebra selects a specific gauge group. The inner fluctuations supply its gauge bosons. The off-diagonal part of the finite Dirac operator behaves like a scalar that couples left and right spinors. That scalar inherits a potential from the spectral action. It plays the role of a Higgs field without being inserted by hand. Masses, mixings, and symmetry breaking patterns are encoded in spectral data rather than drawn as supplementary terms. The same machinery controls how couplings are related at high scales. Because the spectral action counts eigenvalues with a single cutoff, gauge couplings begin life-aligned. Their later running under renormalization spreads them apart in the familiar pattern. Fermion mass matrices enter as entries of the finite Dirac operator, and neutrino masses gain a natural place through heavy sterile states whose presence is spectral rather than speculative. Early fits of parameters offered bold numbers that were later revised as higher order corrections and experimental updates arrived. The deeper point remains. A broad slice of particle physics and gravity can be phrased as a single statement about spectra. A different incarnation of non-commutativity starts from a simple commutator among coordinates. Let two spatial coordinates obey x times y minus y times x equals I times a constant with dimensions of area. Replace ordinary multiplication by a star product that encodes this rule. The result is a flat world where points are smeared into cells of minimal size. Momentum space remains classical, but position space acquires its own uncertainty. Plane waves still exist. Fields still carry quanta. Feynman graphs still contribute. Yet ultraviolet divergences are warped into a peculiar trade with infrared behavior. Tiny loops seed, long-distance tails, a mixing that challenges ordinary expectations and demands new renormalization strategies. Gauge theories live on such spaces after a careful translation. Parallel transport becomes star unitary. Field strength is still a commutator, but it is computed with the deformed product. There exists a map that expresses non-commutative gauge fields in terms of ordinary ones plus an infinite tower of higher dimension operators whose coefficients are fixed functions of the non-commutative scale. This map preserves gauge equivalence and provides a way to compare with data. Observational bounds then press the non-commutative scale far above energies seen so far if the deformation violates ordinary Lorentz symmetry. Variants that implement symmetry in a twisted manner soften this pressure, but still carry strong constraints. Finite matrix algebras give a complementary picture that is better suited to compact spaces. A sphere, for example, can be approximated by large matrices with commutators that mimic the angular momentum algebra. As the matrix size grows, the spectrum of the Laplacian approaches that of the smooth sphere, but at any finite size the number of modes is finite. The geometry is fuzzy rather than sharp. This fuzziness acts as a spectral regularization that preserves rotational invariance and tames ultraviolet behavior without a rigid lattice. Landau-level physics in strong magnetic fields offers physical motivation for such fuzziness, since guiding center coordinates acquire non-commuting brackets in that regime. Matrix models push the idea further and place matrices at the foundation. The dynamical variables are large Hermitian matrices, one for each spacetime direction. Their action penalizes non-commutativity through a trace of double commutators. Classical solutions describe extended surfaces where the matrices approximate coordinates on branes. Fluctuations around such solutions look like gauge fields and scalars that live on those branes. In some regimes, an effective notion of gravity appears from collective excitations and from the way fluctuations couple to the trace of the energy-momentum tensor. Space and matter emerge from algebra in a shared breath. Curvature in the spectral setting is a property of the Dirac operator, rather than of a metric tensor. The heat kernel of the operator captures how a wave packet diffuses. Short-time coefficients in that kernel expansion are integrals of scalar invariance built from curvature and gauge fields. Long-time behavior probes large structures and topology. The adage that one can hear the shape of a drum becomes a working principle. The count of eigenvalues below are high threshold records: volume, area, and integrated curvature. Subtler spectral features register the arrangement of holes and handles. Where two spaces share the same spectrum, they can still differ in shape, but the ambiguity narrows as more spectral data are included. Black holes and cosmology offer imaginative arenas for these ideas. A minimal length implied by non-commutative brackets can smear the would-be point of divergent curvature into a region with finite invariance. Thermodynamic quantities such as temperature and entropy then receive tiny corrections that depend on the non-commutative scale. In expanding universes, spectral actions with running cutoffs generate time-dependent, effective couplings that influence early acceleration or late-time behavior. The language stays the same. Choose an algebra, choose a Dirac operator. Read the physics from the notes they allow. Experiments have not yet found a direct fingerprint, and the search itself refines how the ideas are framed. Any deformation must respect the triumphs of Lorentz invariance across vast baselines. Any spectral unification must meet the detailed pattern of masses and mixings that detectors continue to sharpen. Tabletop platforms emulate the mathematics in condensed matter, where bands and Berry phases create emergent algebras that mimic non-commutative relations. Cold atoms in rotating traps write Moyle products in real light. Electrons in strong fields form droplet states whose edges carry current with a rigidity that speaks the same grammar. These analogues do not prove cosmic non-commutativity. They train intuition for a world where space is an algebraic actor. A philosophical clarity arrives in the end. Points are not sacred. What matters is the algebra of observables and the operator that tells them how to change. Distances are not given. They are answers to constrained questions asked of that algebra. Curvature is not a bend seen by an ideal ruler. It is the spectral bias by which frequencies are populated. Matter is not placed on a stage. It participates in writing the very operator that defines the stage. The picture is both austere and lush. Austere because it replaces pictures by rules. Lush because those rules carry symphonies of spectra that can in principle encode all that rulers and protractors once did. The geometry that refuses to commute does not abolish the world that eyes and instruments describe. It recodes it. A mountain becomes a pattern in the spectrum of a differential operator. A particle becomes a representation of the algebra that defines locality. A horizon becomes a change in the counting of modes. The hope is that by turning the map into music, the mismatches of older maps will quiet. The distances still measure. The curves still guide. The spectra do the talking. A ray of light carries two directions at once, the way a violin string carries both note and harmonic. In 4 dimensions, a massless momentum splits into a pair of spinors, one left-handed and one right-handed, and the split reveals a hidden simplicity. Coordinates that cling to points blur the view, but coordinates that cling to light unwind the tangle. Twister space takes this hint seriously. It trades locations for rays, and it rewrites fields as holomorphic data living on a new canvas. Points of ordinary space become complex lines, null geodesics become points, and solutions of free field equations appear as contour integrals. Incidence relations stitch the two pictures together with a single linear rule, a quiet bridge between geometry and light. The reward of this exchange is a grammar in which helicity is natural and conformal symmetry is manifest. A positive frequency wave of definite helicity becomes a simple object in twistor space, one that can be summed or multiplied without dragging along the burdens of gauge redundancy. Interactions, once drawn as crowded diagrams of virtual particles, begin to rearrange into patterns that look less like combinatorics and more like geometry. Even before the first calculation is finished, a mood settles in. Perhaps scattering has been asking to be described where rays, rather than points, are primary. A decisive turn came from a string theory placed not in space-time but in twistor space. Worldsheets map to curves whose degree measured helicity content, and the simplest multi-particle processes condensed into a single rational function that fit on one line of a chalkboard. What once demanded pages of diagrams collapsed into a tidy pattern of spinor brackets. The breadth of the simplification was shocking. It did not abolish complexity, but it relocated it, as if a heavy cabinet had been slid onto rollers. Recursion relations deepened the clarity, deformed two external momenta into the complex plane while keeping them on shell and momentum conserved, then let the amplitude be reconstructed from its poles and residues. Each factorization channel supplies a term, and the sum of those terms rebuilds the full answer. The only inputs are lower point amplitudes and the universal behavior near poles. Locality and unitarity are not put in by hand as rules for internal lines. They emerge as analytic consequences of the deformation. The method is surgical, and its knives are spinors. Planar problems in a maximally supersymmetric gauge theory revealed even more symmetry than the Lagrangians suggested. Alongside the usual conformal invariants lived a dual partner acting on variables related to cumulative momenta. Organize momenta as edges of a polygon in an auxiliary space. Then assign to each vertex a momentum twister, a refined coordinate that captures the dual symmetry cleanly. Scattering becomes the geometry of polygons in this twisterized kinematic space. Null edges are automatic. Collinear limits are corners meeting. Loop variables are lines threaded through the polygon's interior. The algebraic clutter retreats. Hidden symmetries stand up and announce themselves as linear actions on momentum twisters. A new object crystallized from this progress, a convex body living in the space of these twisters. Its interior represents allowed kinematics dressed with helicity data. Its facets capture the places where particles go on shell or cluster into subsets that scatter among themselves. The object is positive in a precise sense. It is built from matrices whose ordered minors are all non-negative. The amplitude is not a sum over paths or a trace over states. It is the canonical differential form with logarithmic singularities on the boundaries of this positive body, and no singularities elsewhere. The volume, in an algebraic sense, is the answer. This convex body carries a name that sounds like a promise. Its triangulations correspond to specific recursion schemes. Each simplex in a triangulation yields one term, and the sum over simplices gives a representation of the full amplitude. Choose a different triangulation, and the terms change, yet the total remains the same. Spurious poles appear in intermediate pieces and cancel in the end, because the facets that created them were internal. Physical singularities live only on the outer faces, and there each coefficient is positive. Causality and unitarity, once enforced by summing innumerable diagrams, are recast as properties of a single geometry with healthy boundaries. Loops do not break the spell. Additional variables appear that play the role of lines in momentum twister space. The positive body extends into extra dimensions and acquires new facets that encode unitarity cuts. The all-loop integrand is again a canonical form, with logarithmic singularities only on the allowed boundaries. Checking an integrand against countless cuts becomes checking that the form is the unique one with the required poles and residues. The economy is startling. An ocean of algebra is distilled into a statement of positive geometry. On-shell diagrams and the positive Grassmannian supply the combinatorial scaffolding. Each diagram is a patch of the Grassmannian where all ordered minors are positive. Gluing diagrams corresponds to sewing patches. Cells of this positive manifold map to regions of the convex body. Labels that once looked arbitrary turn out to be coordinates adapted to positivity. Cluster algebras hover in the background, suggesting that the kinematic functions that appear, including polylogarithms at low loop orders, organize into families controlled by algebraic mutations. The mathematics is not decoration. It chooses the alphabet in which answers naturally write themselves. Symmetry takes a regal stance in this setting. Ordinary transformations, dual partners, and their infinite towers assemble into a single integrable structure. The amplitude is an eigenobject of that structure, and the convex body is the stage on which it acts. Infrared subtleties are tamed by factoring out universal soft behavior, after which the finite remainder obeys the same geometric rules. Wilson loops drawn around the polygon's edges compute the same function as the scattering process, a duality that ties color flux at strong coupling to particle exchange, at weak coupling through the shared language of twistors. Gravity hovers near the circle of light. Its amplitudes, built from squaring gauge theory data in intricate ways, inherit simplifications that twister and momentum twister tools make tangible. Singularities arrange themselves with a restraint that Feynman graphs would not have predicted. Double copies of positive geometries have been proposed, not yet with the closure enjoyed in the gauge case, but with enough structure to tempt. If the simplest gauge arena admits a jewel-like convex body, perhaps gravity's arena admits one too, cut from another facet of the same quarry. The reach of positive geometry has already travelled beyond pure scattering. Correlators, form factors, and even cosmological wave functions have found cousins called cosmological polytopes, bodies whose canonical forms reproduce probabilities for fluctuations in expanding backgrounds. The method suggests that where locality and unitarity meet, a positive shape waits to be found, and that the singularities nature permits are precisely the facets of that shape. No collision in a detector knows about twistors or convex bodies. It knows only rates and angles. Yet the theory that predicts those rates and angles becomes sharpest when it listens to the music of light rather than to the footsteps of particles crossing points. The machine for prediction has retained locality in the answers, while discarding it as a principle in the intermediate steps. Recursions and positive forms, spinors and polygons add up to the same experimental numbers, with a fraction of the labour and a surplus of insight. The philosophical echo is gentle and persistent. If a physical quantity that measures a chance of scattering is a volume in a space of abstract directions, then perhaps locality and time are shadows cast by a deeper convexity. The boundaries where amplitudes blow up are not crimes against calculation. They are the honest faces of the shape that encodes all allowable outcomes. The conclusion is not a boast. It is an invitation. When a problem in high-energy physics converts into a question about the facet structure of a positive body, the problem becomes both simpler and clearer. Twistor ideas and their geometric heirs did not merely speed up arithmetic. They changed which questions are natural to ask, and by asking new questions, they found new answers. Heat leaves fingerprints on geometry. A thermometer held by an accelerated observer registers a quiet glow, a warmth that arrives with no furnace in sight. The temperature is set by acceleration and fundamental constants, a hint that horizons and heat are companions. From this companionship grows a daring proposal. Curvature might not be fundamental. It might be the response of many hidden degrees of freedom to the flow of information and energy. In that view, the elegant equations that predict orbits and light bending are not primary laws. They are equations of state. The starting point is local. Around any event, one can draw a tiny patch where physics looks like flat space to leading order. Within that patch, choose a family of observers who accelerate so that a small piece of a null surface behaves as their horizon. Those observers perceive a temperature tied to their acceleration. If energy crosses their horizon, they assign a heat flow to it. Now impose the sober relation that has organized every steam engine since the 19th century. The Clausius rule that heat equals temperature times change in entropy. If the entropy density of that little horizon is proportional to its area, the energy crossing it forces a specific change in area. Demanding that this hold for every such patch drives the surrounding geometry to satisfy the familiar field equations with a cosmological term. The equations become the bookkeeping needed to keep the first law true for all local horizons. The meaning is resonant. Entropy counts microstates, and area, as entropy suggests a vast accounting on every infinitesimal cut through space. If the ledger balances at each cut, curvature must adjust so that heat, temperature, and area always cooperate. Gravity is then the macroscopic elasticity of an unseen fabric, Strain is curvature. Stress is energy momentum. The field equations are the constitutive law that ties them. A complementary message comes from horizons treated as physical membranes. Replace a mathematical boundary by a stretched surface just outside it, and ask how that surface would behave if all exterior fields had to satisfy boundary conditions there. The surface acquires viscosity, conductivity, and a finite heat capacity. Shear on the surface dissipates at a rate fixed by universal constants, and the ratio of shear viscosity to entropy density settles at a simple value that seems remarkably hard to beat. The image is of a horizon fluid that conducts, diffuses, and warms. Curvature is translated into transport. Hydrodynamics extends this translation into a dictionary. Long wavelength disturbances of a hot gravitating system correspond to flows in a fluid with specific transport coefficients. A gently perturbed horizon rings down with characteristic modes. The same data read as diffusion and relaxation in a strongly coupled fluid on a different stage. Pressure, vorticity, and heat flow become geometric language in the bulk description. The universality of hydrodynamics, its indifference to microscopic detail beyond symmetry and conservation, explains why gravitational responses share features across very different systems. They are both entries in the same infrared playbook. Information tightens the circle. Consider the first law of entanglement, which states that for a small change of state, the change in entropy of a region equals the change in the expectation value of its modular generator. For a wedge of space bounded by a plane, that generator is fixed by symmetry and closely related to a boost. If the entropy of the region is computed by a geometric prescription that assigns area to its boundary in appropriate units, then equating the two first laws yields the linearized gravitational equations near that surface. In this derivation, dynamics springs from the obligation that entanglement respond correctly to small disturbances. The quiet command is simple. When correlations shift, geometry must adjust so that the balance between energy and information is preserved. A sharper principle asks for entanglement equilibrium. Imagine a small ball of space that maximizes total entropy when its volume is allowed to fluctuate, while its total energy is held fixed. The condition of maximal entropy forces a relation among curvature, energy density, and the ball's size. That relation matches the field equations to leading order in the ball's radius. The slogan is spare and precise. Space-time arranges itself to keep local entanglement extremal under gentle reshufflings. Gravity is the constraint that protects that extremum. Information can be pictured as a flow, and geometry as the shape that throttles it. In a setting where boundary entanglement equals the flux of imaginary threads through the bulk, the densest pack of threads that can pass without exceeding a fixed local bound defines a minimal cross-section. Where the cross-section tightens, a surface appears whose area computes the boundary entropy. This max-flow min-cut principle elevates the area law from an equation to a mechanism. If threads represent capacity to share information, then the cross-section that limits their passage is the bottleneck of correlation. The bottleneck is also the geometric surface that a ruler would call extremal. Entanglement becomes the engineer of shape. A different line of thought treats gravity as an entropic force. Suppose that a thin screen holds microscopic bits that count area, and that moving a test mass slightly changes the number of accessible configurations on the screen. If the change in entropy per unit displacement is fixed, and the temperature is set by acceleration, the resulting force points toward the screen and has the familiar inverse square profile when the screen is spherical. The picture is provocative. It replaces attraction by a push from statistics. Critiques emphasize the need for a concrete microphysical model and for clear predictions that outrun conventional gravity. The appeal remains that a simple entropy gradient, combined with known kinematics of accelerated frames, reproduces a law written long before information was a scientific word. Thermal language rewrites the cosmic expansion as well. Horizons in accelerating universes carry temperatures. Their areas encode entropy that grows as space stretches. If entropy tracks area and energy is conserved in appropriate senses, pressures and densities must obey relations that echo thermodynamic identities. Dark energy, in that grammar, becomes a bookkeeping term that balances entropies across causal diamonds. The approach is schematic but instructive. It insists that every cosmic ledger include information along with mass and radiation. Laboratory analogues have strengthened intuition. When a fluid flows faster than sound, a sonic horizon forms for acoustic waves, and a faint thermal spectrum appears in the ripples. Cold atoms, optical fibers, and flowing water have all played host to such horizons. The analogues are not substitutes for astronomical data, yet they demonstrate that thermal behavior belongs to kinematics of horizons and not to exotic microphysics. Wherever a boundary hides information from a set of observers, temperature and entropy participate. The open questions are not decorations. What are the microstates that area counts? Are they qubits living on surfaces, or patterns of entanglement in a deeper network, or degrees of freedom of an unknown field? Why is the entropy density so simple? How does one derive the precise numerical coefficient from a unique microscopic theory? What fixes the cosmological term within this thermodynamic logic? How far does the hydrodynamic analogy reach before it breaks? Each question is the kind that makes a good theory stronger by forcing specificity. Still, a pattern is hard to ignore. Temperature appears whenever access to information is restricted by a horizon. Entropy tracks area with rare fidelity. Linear responses of geometry follow from linear responses of entanglement. Transport in fluids mirrors relaxation of horizons. Clausius and Boltzmann whisper rules that geometry seems obliged to obey. If these are coincidences, they are persistent ones. If they are clues, then gravity is the grandest emergent phenomenon yet found, a collective behavior of many microscopic actors whose identities are only partly known. Perhaps the right metaphor is not weight but weather. Pressure gradients move air. No single molecule knows the storm. In the same way, gradients of information move curvature. No single microstate knows the orbit of a planet. The spreadsheet that predicts tides is written in terms of fields and metrics because those are the natural large-scale variables. Underneath, a quieter table is kept, one that counts correlations and insists that erasure has a cost, that heat follows horizons, that equilibrium selects geometry. In that quiet table, gravity is heat, and the universe keeps perfect books. A mirror is lifted to the world, and the image moves in perfect reverse. Yet no mirror coerces a dropped cup back into a standing glass. The laws in their microscopic attire often admit time reversal, while daily life wears an arrow that points from cool dawn to warm afternoon, from unbroken to broken, from memory to anticipation. The puzzle glows in that contrast. If equations nearly respect a reversal of time, why does experience refuse it? And could influence ever lean backward without tearing causality? Many fundamental equations are symmetric under a flip of temporal direction. Classical mechanics, electromagnetism in vacuum, general relativity, and the unitary evolution of quantum states all allow histories to be reversed with a simple change of sign in time and suitable swaps of initial for final data. The arrow that rules kitchens and galaxies arises not from the form of these equations, but from conditions at the boundaries of the story. A simple statement carries weight. The universe began in an extraordinarily low entropy configuration. From that seed, coarse-grained degrees of freedom naturally tumble into disorder, and the tumble writes the thermodynamic arrow that guides weather, biology, and thought. Information deepens the point. When a system becomes entangled with its environment, phase relations leak into inaccessible degrees of freedom. Records form, and those records can be read in one direction with ease, and in the other direction only with precise conspiracies that never occur in practice. Decoherence does not break unitarity. It makes some correlations unreachably fine. Memory, in this light, is a thermodynamic act. To store a bit reliably and to erase it later both require entropy production. The psychological arrow follows the ledger of increasing records. and that ledger follows entropy. A different tradition looks for arrows in the global structure of electrodynamics. Maxwell's equations admit advanced and retarded solutions. Fields could in principle be sourced by charges in the future as well as in the past. Yet the world prefers retarded radiation. One explanation treats the preference as a boundary condition. If the entire cosmos acts as an efficient absorber, advanced effects cancel in a way that leaves retarded behavior as the net result. Radiation then owes its arrow to a global requirement on the ensemble of charges across spacetime. Influence does not violate causality. It respects a rule that spans both ends of the narrative. Quantum theory invites bolder symmetry between past and future. In a framework that conditions not only on initial states but also on final post-selections, probabilities for outcomes depend on both boundary choices. Weak measurements in such settings can reveal statistics that look anomalous yet fit an exact calculus that treats the present as a joint negotiation between what has happened and what will be recorded. No usable message travels to the past, since the post-selection is known only after the fact. Yet the correlations suggest that explanation can be time-symmetric without enabling paradox. An allied image refreshes the conversation. A quantum process can be read as a handshake across spacetime. One set of waves offers, another confirms, and the realized event is the completed transaction. Advanced aspects are part of the handshake, but the completed outcome respects relativistic causality. The picture is a metaphor for a mathematics that is ordinary and unitary, yet the metaphor makes an idea vivid. Correlations can link future and past boundary data without making a channel for sending a warning to yesterday. Other experiments relax even the assumption that events have a definite causal order. In the laboratory, operations can be placed into superpositions of one happening before another and another before the one. Process matrices and the quantum switch implement this superposition of causal arrangements. Tasks that would be impossible with a fixed order become possible. Communication capacities improve under specific constraints, yet no paradoxical influence reaches backward in a way that contradicts relativity. The lesson is precise. Causal order can be indefinite inside a quantum device, while the global arrow outside remains intact. Space-time itself can be cast as a whole, a four-dimensional block in which every event is a fixed bead on a completed thread. In that picture, dynamics is a relation among slices rather than a flow that creates slices. The feeling of becoming is then an emergent feature of records that accumulate along world lines. The equations that govern the entire block are time-symmetric, while the distribution of low-entropy surfaces at one end privileges a direction inside the block. Nothing moves in the block. Yet on any given world line, the density of reliable records increases toward what that world line calls future. The arrow inhabits the pattern of records, not an external clock. General relativity contains solutions in which closed time-like curves appear. Rotating universes, near critical cosmic strings, and wormholes with time shifts are standard exhibits. Such curves seem to invite paradoxes. The resolution most consistent with physics as practiced is to replace paradox by consistency constraints. Histories that would produce contradictions have measure zero. Only those that fit self-consistency occur. In classical terms, this is the Novikov idea. In quantum terms, there exist prescriptions that drive states to fixed points when they traverse such curves, so that probabilities never sum to impossible stories. Other analyses suggest that the attempt to make a curve traversable triggers instabilities and back reaction that destroy the would-be time machine. Chronology protection would then be a dynamical fact, not a separate law. Time reversal is not exact in the weak interactions. Certain decays display asymmetries that imply a violation of T-symmetry when combined with the CPT theorem, a bedrock result of local relativistic quantum field theory that equates CP violation with T violation. The magnitude of these effects is tiny compared to the march of thermodynamic time, yet they matter for the deep issue of why matter dominates antimatter. Baryogenesis demands CP violation, departures from equilibrium, and interactions that change baryon number. The arrow and the asymmetry are siblings rather than identical twins. The difference in abundance owes to microscopic irreversibility in the early universe, while the unidirectional flow of daily life owes to the low entropy past and to the spread of entanglement that hides phase information. Mirrors hold another kind of challenge: reverse parity, reverse charge, and reverse time, and many processes reappear unchanged. Matter has a mirror twin in this algebraic sense, not in the sense of a second world. The precise manner in which these discrete symmetries break or hold has guided the architecture of particle theory and keeps a bench for surprises. Yet the everyday arrow pays them little attention. It continues to follow the broader thermodynamic slope. Could influence ever run from future to past in a way that outpaces light and sends a readable message? Every careful proposal so far preserves a strict no-signaling rule. Delayed choice experiments, quantum erasers, and post-selection reveal that correlations can be arranged so that late decisions sort earlier data into subensembles with different patterns. The earlier detections remain what they were. Only their joint statistics with later settings change. Whenever an effect would enable a paradox, conservation laws, decoherence, or simple causal bookkeeping intervene and close the door. Computation supplies a different arrow that harmonizes with the others. Reversible logic gates exist, and in principle, any computation can be performed with negligible energy cost, if done reversibly and slowly. Yet to discard a bit of information costs heat in the environment. Practical computation needs erasure, and erasure writes a thermal signature that aligns with the passage from ordered input to disordered waste. The device that thinks is a small engine that produces exhaust. Thought even as abstract arithmetic sides with the arrow that entropy sets. Speculation also allows a final condition to influence what happens in the middle, not with messages but with consistency. Some formulations of quantum cosmology consider both an initial low entropy boundary and a final boundary where certain global properties are fixed. Path integrals then weigh histories by how well they fit both conditions. From the inside, observers still see no violations of causality. They discover that records align in a way that reflects a hidden global constraint. The analogy is ordinary action principles. A geodesic between 2 points is the curve that extremizes length given both endpoints. Nothing mystical enters. The whole, when demanded to be simple, trims what the parts can do. In the end, the arrows are many, and they align. Entropy grows in bulk matter. Radiation streams outward from hot to cold. Records accumulate. Biological complexity rides the free energy released as gradients run down. Weak interactions mark a minute asymmetry that helped set initial conditions for chemistry to exist at all. Quantum theory allows boundary conditions at both ends to shape outcomes without permitting theatre-breaking signals to the past. Mirrors reflect, yet cups still shatter. The world keeps its promises with a consistency that makes time feel like a gentle slope rather than a law. If influence ever leans back, it leans as constraint, not as command, and the future participates in shaping the present only through the quiet demand that the whole story makes sense. Imagine a ledger written not in ink but in bits, a ledger that updates itself with every interaction. Matter becomes a pattern of yes and no, fields become streams of symbols, and motion becomes the execution of a program that never halts. In that portrait, the universe is not only described by mathematics, it behaves like a computation. The question is not whether computers can mimic physics. The question is whether physics is itself the act of computing. A physical computation is a process with two faces. On one face, there are states and rules. On the other, there are energies and entropies. A flip of a bit is also a flip of a physical system between two distinguishable configurations. If a bit is erased, heat must be released into an environment to keep the books balanced. The price of forgetting is temperature times a constant times the number of bits discarded. Memory is never free. Logic is never abstract. Every algorithm must rent space in matter and pay its bills to thermodynamics. Reversible logic turns the analogy into a near identity. A gate that never discards information can run forward or backward with equal fidelity, and in principle it can operate with arbitrarily little heat so long as it moves slowly. The dream logic of perfect reversibility is a physics lesson in disguise. Microscopic dynamics are often reversible, and macroscopic irreversibility arrives only when information is thrown away into inaccessible degrees of freedom. A grand, reversible computer the size of a planet would still warm its surroundings if it compressed or erased data. Yet if it uncomputed every intermediate record, it could reduce the heat it leaves behind to a whisper. Quantum theory raises the stakes. A qubit is not only a 0 or a 1, it is any superposed combination the rules allow. Entanglement knits qubits so that the whole stores correlations no part can carry alone. A circuit of unitary gates unfolds, a computation that is deterministic in its amplitudes and indeterministic in its outcomes, a paradox only on the surface. The power of such circuits comes from interference. Paths cancel or reinforce one another, and some problems are solved with fewer steps than any classical circuit could hope to manage. The device is still a piece of matter, subject to noise and loss, so fault tolerance must be woven in. Error correction embroiders logical qubits across many physical ones and hides information in global patterns that local perturbations cannot easily spoil. The result is a new kind of condensed matter, a phase whose order is not a pattern in space, but a pattern in how information is stored. There are speed limits and storage limits that ignore human technology and speak to nature itself. A finite region with finite energy can perform only so many logical operations per unit time, no matter how cleverly arranged. A bounded system can store only so many bits before gravity takes notice and squeezes. The densest possible memory for a given area is a horizon. The most feverish possible clock for a given energy ticks at a rate fixed by the quantum of action. If every process is a computation, then these limits are the universal clock rates and disk quotas that nature enforces without negotiation. Complexity enters as a new measure of time. Two states can have the same entanglement, yet one can be deeper within the catalogue of circuits. Depth is the minimal number of simple gates needed to build the state from a chosen reference. In many body systems, the depth keeps growing long after other observables settle near equilibrium. From the outside, little seems to change. Inside, the state marches into regions of Hilbert space that are staggeringly remote from the origin by any sequence of simple operations. That march is slow to reverse. The return would require gates arranged with a conspiracy that noise and practical limits almost always forbid. Complexity is a second arrow that points towards states hardest to unscramble. Models that build worlds from rules illustrate both promise and restraint. In a cellular automaton, a grid of cells updates by local instructions, and yet can display gliders, collisions, and reproduction. Simple programs give rise to intricate behavior that no quick shortcut can predict. The only way to know what happens after a long time is to run the evolution step by step. This feature is called computational irreducibility. If such irreducibility is common in fundamental dynamics, then forecasting distant outcomes from compact formulas may be impossible in principle, even if the rules are known. Prediction would not fail because information is missing. It would fail because the shortest route to the answer is the universe itself. Algorithmic information theory offers a second lens. The complexity of a string is the length of the shortest program that prints it and halts. Regular patterns have short descriptions. Random strings do not compress. The laws of physics, viewed as programs, are short, which is why they feel beautiful. The initial conditions, viewed as input data, can be long and messy. One cannot assume that the cosmos chooses the shortest possible description of its particular history, only that the rules that map histories to predictions are compressible. This difference explains how a compact set of equations can generate a sky crowded with irregular galaxies and a biosphere noisy with contingency. Computation does not erase continuity. Fields and wave functions evolve smoothly, yet their measurable content is finite because measurements discriminate among finite alternatives with finite accuracy. A detector clicks or does not. A clock returns one of many possible digits. The analog is handled as the digital at the moment of record. The grain enters at the boundary between model and observation. This boundary is not arbitrary. It is set by the unavoidable fact that distinguishing more than one bit requires more than one unit of energy and time. If physical law is an algorithm, then symmetries are optimizations. A conserved quantity prevents the program from recomputing what is already known. A gauge redundancy strips away superfluous coordinates and keeps only the DOF that change outcomes. Renormalization is a compiler that removes dependence on microscopic detail when asking macroscopic questions, yielding effective codes that run faster because they ignore lines that do not matter at large scales. The same compiler can run in reverse, revealing how parameters modify when one targets finer and finer resolutions. A translation between high-level and low-level descriptions. Observation becomes an I/O problem. A region segregated by a horizon becomes an isolated device with limited input channels and bandwidth capped by area. The outside cannot learn more than the channel permits, and the inside cannot signal more than the boundary allows. The bookkeeping of bits across that cut explains why heat appears when information is hidden, and why lossless recovery requires resources that grow quickly with system size. The feeling that something vanishes is often the feeling that a channel is too narrow to return it. If the cosmos computes, it does not compute in the tidy style of human software. There is no global clock that steps through lines in strict sequence. There is no central processor. There is no external debugger. The execution is fully parallel and fully local. Each small patch updates according to nearby influences, and consistency is enforced where patches meet. The correct picture is closer to asynchronous distributed computing than to a desktop machine. Deadlocks are forbidden by causal structure. Race conditions are tamed by relativistic constraints. Final results are encoded as invariants that all observers agree upon, even when they disagree about the order of events. Dissent has important points to make. A metaphor is useful until it claims sovereignty. Not every flow resembles a logic gate. Not every field is best imagined as a register. Not every law reduces to code. There are aspects of explanation that reside in geometry, in symmetry, in variational principles that feel less like algorithms and more like music. Yet even those aspects can be reinterpreted in computational terms when pressed. A variational principle is a search through histories for the one that extremizes a cost. A symmetry is a compression that groups many stories into one. A geodesic is the shortest path not only in length but in the program that describes motion under constraints. Speculation flowers where caution allows. Perhaps every subsystem that can compute in principle is also a subsystem that can simulate a patch of the world with bounded resources, and perhaps the ultimate limits of simulation coincide with the ultimate limits of prediction. Perhaps the difficulty of building a universal quantum computer is not an accident of engineering but a protection that stabilizes macroscopic reality from easy rewrites. Perhaps complexity is a hidden conserved quantity in broad regimes, rising on average and falling only under rare, fine-tuned manipulations. Viewed this way, existence is not a collection of objects but a cascade of updates. Stars compute the fates of their cores as they burn and cool. Crystals compute their own symmetries as they grow. Living cells compute gradients of nutrients and the edits of their genomes. A mind is a computation that models other computations while being modeled in return by a world that supplies its inputs. The universe computes itself into the next moment, and the program it runs is the collection of lawful relations that never yet failed a test. At midnight, the laboratories listen. Lasers idle at line center. Vacuum chambers hum with the thinnest breath. Test masses float behind gold shields while seismic feet soften the rumble of the earth. What these machines hope to hear is not a shout but a rumor. Somewhere beneath shot noise and thermal jitter, beneath the shrug of mirrors and the slow flecks of glass, lie hints that space-time carries a grain, or that gravity speaks in quantum syllables. The instruments do not demand a revelation. They ask for a whisper that can be measured twice. Interferometers are the flagship listeners. Two long arms hold light between mirrors until the paths are so coherent that a displacement smaller than a proton's width changes the brightness at the photodiode. Sensitivity at that scale is a negotiation with quantum mechanics. Photons arrive like raindrops that patter on the mirror with random force, and counting their arrivals gives the meter its ultimate fuzz. Push power up to reduce counting noise, and the radiation pressure kicks grow. Pull power down, and the counting noise returns. To bend this trade, a second beam is prepared in a special state whose fluctuations are squeezed along one quadrature and stretched along the other. Injected at the dark port, it tips the balance and quiets the noise where the measurement lives. Microkelvin coatings trim thermal motion. Cryogenic designs shelter mirrors from Brownian drift. Filter cavities rotate the squeeze with frequency, so the help arrives exactly when needed. Quantum back-action becomes a design target rather than a limit. Readout schemes are devised to sample the velocity of a mirror instead of its position, sidestepping the commutator that foils repeated position measurements. Correlations between shot noise and radiation pressure are engineered, so back-action subtracts itself. Suspensions become sculptures of fused silica that isolate mirrors from ground motion while introducing almost no loss of their own. Even the atmosphere is kept outside, for air refracts light with its own flicker, and the faintest eddies would mask the signal that a merger in a distant galaxy writes on the beam. Where light is too large, atoms take its place. Cold clouds are launched in fountains, split into superposed paths by pulses of laser light, and allowed to fall. Atomic phase accumulates from gravity and acceleration, then recombines to yield fringes. Sensitivity grows with the square of interrogation time and with baseline. Two such fountains placed apart and interrogated with the same lasers can form a gravity gradiometer that reads tidal fields directly. Using two atomic species in the same instrument allows tests of the equivalence principle that compare how different masses fall. The attraction is relentless. If universality fails even slightly, a phase will drift between the two clouds that no clever calibration can fake. Optical clocks extend the reach of precision into time itself. A single ion, or an ensemble of neutral atoms trapped in an optical lattice, ticks at a frequency in the petahertz range, with line widths slim as a thought. When two such clocks are compared through stabilized fibers, their rates agree to parts in 10 circumflex 18. The difference in gravitational potential between two shelves in the same room can be read as a difference in time. Networks of these clocks promise a new style of geodesy in which mountains and aquifers are mapped by their effect on ticking rather than by levels and plumb lines. Tie clocks across continents, and the global potential becomes a dial that responds to tides, to groundwater, to the slow, isostatic rebound of ice lost centuries ago. Clocks can also listen for long, slow undulations of spacetime. If two or more spacecraft carry clocks linked by optical links with phase-stabilized lasers, a passing wave will stretch and squeeze the light travel time among them. The trick is to place the clocks in drag-free flight, where small thrusters cancel every gust of solar wind and every photon recoil, leaving the clock's heart to drift in near-perfect freefall. Arm lengths measured in millions of kilometers put the experiment in a band where supermassive binaries sing and where cosmological relics might hum. The technology is a discipline of calm. Phasimeters temper laser noise by transcribing it into known combinations that cancel. Capacitive sensors cradle test masses without touching them. The void supplies the vacuum that no pump can match. At the lowest frequencies, stars themselves are the clocks. Pulsars keep time with a stability rivaling atomic references. Arrays that time many pulsars and compare their residuals across the sky can discern a quadrupolar pattern that announces a background of nanohertz gravitational waves. The timing records must be scrubbed of every terrestrial irregularity, from changes in planetary ephemerides to the whisper of interstellar plasma that swells and thins. What remains can reveal a chorus from countless slowly inspiraling pairs. The array does not image a single source. It hears the weather of space-time on the widest scales. Detectors also aim at faint cosmological fingerprints. Polarization in ancient light can carry a curl pattern that is not sourced by density alone, a pattern that would be the scar of gravitational waves laid down in the first instant, after expansion pulled quantum ripples to cosmic scales. Telescopes that scan dry, cold skies watch for the curl, while fighting the polarized glow of dust that the galaxy contributes. Spectrometers look instead for tiny deviations from a perfect blackbody spectrum, distortions that freeze in when energy is injected into the primordial plasma and cannot be fully erased. Each deviation remembers a time and a mechanism. Each is a whisper from an epoch that no telescope can photograph. Tabletop experiments push at gravity from the short side. Torsion balances compare the pull-on test masses arranged in patterns that would cancel ordinary inverse square fields, but would respond if an extra range or a new charge were present. Microcantilevers approach source masses to distances where quantum vacuum forces complicate the ledger. Carefully chosen materials, shielded geometries, and modulated motions distinguish between known attractions and unknown ones. Any deviation from the anticipated torque would be a clue that new degrees of freedom have crept into the low-energy world, perhaps those that screen themselves in dense environments and break, hiding only in the thin cold of a laboratory. Optomechanics seeks quantum behavior in objects heavy enough to feel their own gravitational field. Tiny membranes, nanobeams, and levitated spheres are cooled by light and feedback to their motional ground states. Once cold, they can be entangled with light or with each other. The ambitious dream is to place two mesoscopic masses in a superposed or entangled state and let only gravity couple them. If entanglement appears where no other force can mediate it, gravity will have been caught wearing quantum clothing. The technical mountain is steep. Environmental force noise must be tamed below the feeblest whisper. Casimir tails must be screened without adding thermal clutter. Magnetic and electric patches must be neutralized until only the slow mutual tug remains. Antimatter offers another quiet probe. Neutral antiatoms can be cooled, trapped, and allowed to fall. A trajectory recorded with microkelvin precision compares their acceleration with that of ordinary matter. Any difference would rewrite a chapter of equivalence and invite new symmetries to explain it. Achieving neutrality, suppressing stray fields, and shaping magnetic gradients into a transparent lens demand patience that stretches over years. The result is simple to state. Do all things fall the same way? The answer will be measured, not argued. Quantum metrology threads through all of these efforts. Ensembles of atoms are prepared in spin-squeeze states that push phase noise below the standard limit. Light is entangled across modes so that common noise cancels in differential measurements. Correlated detectors are separated by baselines large enough that local disturbances subtract while a global signal adds. Every physical principle that suppresses fluctuations without sacrificing signal is recruited. The idea is not domination by cleverness. It is generosity to the data. When nature speaks softly, the experiment must quiet every voice in the room that is not hers. Noise itself becomes a field to be measured and removed. Seismometers surround interferometers to subtract Newtonian gravity gradients from surface waves that would otherwise tug the test masses directly. Microphones and anemometers map infrasound and temperature streaks that bend beams by changing refractive index. Magnetometers track local storms in the geomagnetic field. Synchronized networks compare residuals, so an event that touches them all can be distinguished from an event that haunts only one. Every subtraction is a conversion of ignorance into information. Every removal of noise is an admission that the world is talking loudly about other things. No instrument will shrink to the Planck length. The ambition is more patient. Build a web of detectors that together constrain how smooth, how linear, how local the world remains, as energies rise and distances fall. Tie clocks until redshift can be read across a human stride. Chill mirrors until quantum pressure is the loudest tap on their backs. hold masses so still that a whisper of entanglement could cross between them without help. Listen to pulsars until their common murmur becomes a map. When the whisper arrives, it may be a change of slope in a noise spectrum, a tiny failure of universality, a correlation that should not be there, a drift in a line once thought straight. Instruments tuned for patience will be ready. They are already asking the right kind of questions, with ears made of light, of atoms, of clocks, and of silence. A faint blue fire surrounds the planet every night. It arrives from every direction with nearly the same chill and nearly the same hue, a black body as smooth as mathematics will allow. Inside that smoothness live ripples 1 part in 100,000, and inside those ripples live the fingerprints of forces that touched the cosmos when it was younger than a heartbeat. The afterglow is an archive. Temperature maps sketch the first acoustic notes of matter and light. Polarization maps trace how those notes were scattered into patterns too delicate for any other messenger to carry. Read well, the archive can approve or dismiss stories about the first instance with a few quiet numbers. In that archive, polarization is the sharpest pen. Thomson's scattering turns gradients of radiation into swirls on the sky that separate into 2 kinds, one shaped like ridges and valleys, one shaped like corkscrews. Density waves alone draw only ridges and valleys. True corkscrews demand a field that stretches and squeezes space itself. A detection of a primordial corkscrew pattern would report that gravitational waves were launched while the plasma was still a fog, and it would set the energy scale of that launch by the amplitude of the twist. Lensing by later structures can masquerade as corkscrews by distorting ridges, and dust grains aligned by magnetic fields can paint imposters in milky clouds, so the audit must sift painstakingly. Yet the prize is specific. A non-zero tensor fraction with the right spectrum would favor a mechanism with superluminal expansion and rule against classes that cannot source a broad, nearly scale-free background of waves. The temperature field itself remembers a drum. Before atoms formed, photons and baryons acted as one fluid. Gravity pulled, radiation pushed back, and sound waves rang. At decoupling, the music froze into a pattern of peaks and troughs at angular scales set by the sound horizon. The heights and positions of those peaks already report the geometry and content of the universe with exemplary precision. Beyond these established lessons lie subtleties that probe the beginning. A step or oscillation hidden in the initial spectrum would point to a brief episode when the driving field changed speed, or when it brushed against another heavy field that left an echo. Small, persistent wiggles could betray relic periodicities in a potential. A gentle bend in slope across decades of scale would push models that claim exact scale invariance into the corner. Statistics of triangles in the sky carry a separate verdict. If the generator of the first fluctuations was a single, slowly rolling degree of freedom in a vacuum state, a relation links the behavior of the 3-point function when one side of the triangle is very long compared to the others. Violate that relation by measuring a squeezed signal too large, and the story must be revised. Different shapes of non-Gaussianity point to different microphysics. A shape that peaks for equilateral triangles suggests interactions with higher derivatives. One that prefers flattened triangles hints at excited initial states. A trispectrum that refuses to factorize could reveal fields that were heavy during the first instance and left their signatures as phase-dependent ripples, a cosmological collider where masses are measured by interference rather than by bump hunts. Not all primordial disturbances tilt energy densities. Some reshuffle species at fixed total energy. Such isocurvature modes are natural if additional fields produce relics that do not immediately share thermal histories. Axion-like particles born from misalignment are a canonical example. The afterglow can discriminate. Isocurvature leaves a distinct phasing of peaks and a different pattern in polarization. Bounds on these modes already narrow the room for such relics, and any positive detection would force a revision of how the inventory of dark matter formed and when it began to clump. The afterglow can also rotate its own light. A slowly varying field, with a pseudo-scalar coupling to electromagnetism, twists polarization by an angle that accumulates along the line of sight. A uniform twist mixes ridges and corkscrews across the sky and can be read as a global parity-violating tilt. A varying twist produces curl patterns that correlate with temperature in ways forbidden by ordinary physics. Faraday rotation by primordial magnetic fields can mimic some of these signatures at low frequencies, but with a frequency dependence that separates the two. A confirmed rotation with the wrong chromatic behavior would be a quiet proclamation that a new, nearly massless field is drifting through the cosmos. Where temperature and polarization respect a perfect blackbody, the spectrum adds another test. Processes before recombination damp small-scale ripples by diffusion and inject their energy into the photon bath. If the injection occurs when interactions still reshuffle photons efficiently, the bath rethermalizes. If it occurs slightly later, a chemical potential distortion freezes in. Later still, a Y distortion records heating without changing photon number. The amplitude and angular correlation of these tiny departures from a perfect Planck curve carry a record of small-scale power and of energy injection from decays, annihilations, or exotic events, such as cusp radiation from thin strings. A positive mu signal at a level larger than predicted by damping alone would announce extra small-scale structure in the primordial spectrum or late decays of fields, light enough to survive well beyond the earliest plasma. Recombination itself is not a featureless blur. Two photon transitions in hydrogen and helium, radiative transfer through Lyman lines, and the tiny populations of excited states determine exactly when the fog clears. A deviation in fundamental constants, even a tiny drift during that era, would shift the timing and line profiles and leave correlated changes in peaks and in damping scales. Emission lines from recombination are predicted as faint spectral features spread across radio to far infrared bands. Detecting them would lock the atomic history in place with laboratory accuracy and make any departure from standard microphysics glaring. Later, reionization repaints the map by partially rescattering the light. The overall optical depth damps small-scale power and adds a large-scale bump to polarization. Patchiness during the era of first stars produces secondary curls and Doppler imprints known as kinetic Sunyaev-Zeldovich signals. The statistics of these secondary marks, correlated with galaxy surveys, can isolate how structure grew and how heat leaked into the intergalactic medium. Models that screen new forces in dense environments but act in the diffuse cosmos leave telltale changes in growth rates that lensing of the afterglow can recover. Lensing itself is a painstaking sculptor. Matter between us and the last scattering surface deflects light and remixes ridges into corkscrews. From that remixing, one can reconstruct a map of projected gravitational potential across the sky. The amplitude and scale dependence of this lensing power measure the sum of neutrino masses by reading how free streaming particles suppress growth on small scales. Extra light relics that were present during radiation domination shift the phase of acoustic peaks and the lensing amplitude together. The combination provides a lever arm strong enough to test ideas about hidden sectors that never thermalized with ordinary matter. On the largest angles, curiosities persist. The quadrupole sits low. Certain multipoles appear aligned in a way that tempts the eye. One hemisphere seems to prefer slightly stronger fluctuations than its opposite. Each feature hovers near thresholds where cosmic variance and a posteriori statistics argue for caution. Still, if a simple extension of the initial conditions consistently sharpens these alignments without breaking the rest of the fit, an anomaly could graduate into a clue. Large angle parity violations, say, or a dipole modulation of power, could hint at a remnant of pre-inflationary structure or a coupling to fields that chose a direction in the deep past. Beyond the microwave band, hydrogen's 21 centimeter line promises a dimensional extension of the archive. Before the first stars, neutral hydrogen traced density with a clean bias and no astrophysical heating. Fluctuations in its brightness temperature across the sky and along redshift encode a three-dimensional power spectrum of the Dark Ages. unexpected excess absorption against the radio background, unusual timing of the first heating, or a suppressed small-scale power spectrum would each signal new interactions, warm components in the dark sector, or early injected radiation. Cross-correlating this tomographic map with polarization and lensing of the afterglow would triangulate on any discrepancy with ruthless efficiency. A final set of signatures turn on symmetry itself. If gravity in the early universe violated parity, the afterglow would carry temperature, curl, and ridge, curl correlations that are forbidden otherwise. If a helical magnetic field stretched across cosmic volumes, it would imprint handedness in polarization that changes with frequency in a predictable way. If spatial curvature deviates from zero by a hair, the spacing of peaks and the statistics of modes separated by large angles would lean together. These effects are small, yet the archive is patient. Every year, the maps sharpen. Nothing in this audit requires guessing names. It requires careful counting of patterns in an ancient light and a willingness to let a microkelvin decide among grand proposals. Each feature the archive can reveal has a unique translation. A tensor amplitude points to a high-energy origin for the first ripples. A squeezed triangle beyond a limit points to extra fields. A mu distortion larger than damping alone points to power or to decay. A rotation points to a drifting axion-like field. A non-zero sum of neutrino masses points to the mass scale written in cosmic structure. The afterglow will not deliver a manifesto. It will deliver a ledger of small, precise entries. Theories that cannot balance that ledger will be retired. The one that can will inherit a sky that has spoken softly and been heard. A chalkboard fills with lines that curve like calligraphy, and eyes soften because the shapes feel inevitable. Beauty has a way of leaning forward inside a mind trained to look for order. Symmetry calms, simplicity promises, unification hums like a chord that resolves at last. Yet instruments answer to neither serenity nor promise. They answer to what is there. Between the line that pleases and the number that measures sits the art of judgment, the quiet craft by which a community chooses which ideas to pursue, which to set aside, and which to carry while admitting that the verdict is not yet written. Aesthetic criteria have guided discovery more than once. Equations that keep their form under rotations gave charge and spin their dignity. The requirement that laws hold in any coordinate system brought curvature to the stage, demanding that quantum rules and special relativity share a home-placed antimatter in a cloud chamber before anyone had seen it. These are episodes where elegance and truth shook hands. They are also reminders that elegance is a tool, not a warrant. The same love of symmetry can linger over sterile constructions that fit no world, and the same hunger for minimality can discard a necessary complication before it speaks. The simplest rule for choosing among stories says that the shorter description wins. Occam's razor is not a taste for austerity. It is a principle about compression. A model that explains many facts with fewer adjustable numbers is a better compressor of data. Algorithmic information theory turns that idea into arithmetic. The best explanation is the program that reproduces what is known with the fewest instructions. No one can compute the exact length of that ideal program for a universe. Still, the spirit survives in practical statistics. Penalize extra parameters unless the fit improves enough to warrant them. Reward parsimony when two descriptions cover the same ground. Bayesian reasoning builds parsimony into the scaffold. A prior that favors simplicity biases updates toward models that compactly summarize the evidence. Model evidence weighs how well a story predicts what is seen after averaging over its parameters. The average drops when possibilities are spread thin across wide ranges. Surprising accuracy is rewarded. Baroque flexibility is not. This is not an aesthetic decree. It is the bookkeeping of probability that insists prediction must be paid for with credible constraints. Another practical philosophy keeps score across time rather than across models. Research programs have a hard kernel of commitments and a protective belt of auxiliary hypotheses that shield the kernel from refutation. The belt is adjusted when experiments surprise. A program is progressive if those adjustments lead to fresh predictions that are confirmed. Degenerative if they only patch wounds without new successes. The diagnosis is not a sentence. It is a warning light that flashes when improvisation outstrips discovery. Coherence places a separate weight on the scale. A candidate that meshes with many independent facts gains credit that no single test could grant. Matching precision gravity in the weak field, reproducing quantum field theory at accessible energies, fitting astrophysical surveys, and agreeing with laboratory tests are not independent tasks for an ambitious idea. They are thresholds that a final account must cross. Dualities that reveal hidden equivalences, renormalization flows that knit scales into a single fabric, and consistency conditions that hold across frameworks are all signs that an idea respects the architecture of physics rather than leaning on a single spectacular prediction. Fertility matters as much as fit. A good idea grows consequences. It calculates things that were previously opaque. It suggests new instruments, not only new interpretations of old data. It binds distant subfields with a shared technique. It illuminates mathematics that did not ask to be helpful. When a framework invents tools that later become standard across topics, fertility has paid its debt. When it only generates vocabulary and leaves calculations untouched, caution is healthy. Naturalness sits at the center of many current arguments. Numbers without explanation that must be dialed to extreme precision feel untrustworthy. If small scales are threatened by corrections from large ones, a symmetry that protects the small looks like wisdom. When that symmetry fails to appear, one may search for a new protector, or accept that selection effects in a large menu of possibilities favor the observed value, or judge that the discomfort is a feeling from a previous era and not a rule. Each path carries risks. Protection by symmetry makes predictions only if the symmetry leaves scars near reachable energies. Environmental selection makes predictions only if the population of possibilities and the measure on it can be calculated. Abandoning the worry risks complacency. The tension will resolve only when a testable auxiliary claim steps forward. Null results should not be read as silence. They carve the space of ideas into smaller and cleaner shapes. There is dignity in a measurement that returns nothing where something might have been. Precision electric dipole searches press on hidden sources of time reversal violation. Spectrometers force direct limits on light relics. Interferometers refuse to hear exotic stochastic signals. Each quiet report narrows room for error. Each constraint redirects creative energy toward corners that remain. The psychology of collaboration cannot be ignored. Large promises attract large crowds. Careers migrate with the tide. Credit systems can reward safe contributions to popular programs more than risky leaps in unfamiliar directions. The health of a field depends on a plurality of bets. Agencies that keep small lines open for heterodox work protect the unexpected. Journals that welcome careful negative results draw a map as valuable as one dotted with peaks. Seminars that invite dissent without injury keep imaginations limber. The sociology that makes science human must be managed so that the science remains science. Computation is now a participant in judgment rather than a servant. Symbolic engines test algebra that once took months to verify by hand. Proof assistants check identities in amplitudes and index gymnastics in compactifications. Machine learning finds patterns in parameter scans that would be invisible to a single researcher. Algorithmic discovery cannot choose a question, but it can warn that a cherished intuition sits on a ridge surrounded by valleys of contradiction. The human role shifts toward framing, toward deciding which structures deserve exploration, and toward insisting that an answer is not only accurate but interpretable. There is also a duty to make predictions that risk being wrong within a human time span. A framework that improves endlessly without exposing a foothold for a clear test may be a philosophy rather than a theory. Patience is part of the craft, because some scales are far and the ladder to them is long. Still, risk is the price of progress. A calculation that puts a number where a detector can check it honors the compact between idea and instrument. Even a single crisp inequality, well posed and reachable, is a pledge that criticism is welcome. Interpretation should be restrained by operational clarity. Metaphors carry intuition across gaps, but a metaphor that cannot be cached as a measurement loses value quickly. A bridge between entanglement and geometry is inspiring. It must become a procedure for computing a spectrum or a cross-section. A picture of space as computation is illuminating. It must sharpen into a bound or a design for an experiment. Beauty earns trust when it writes down an algorithm that returns the numbers on the screen. The list of virtues is long, and none is sovereign. Simplicity without reach is brittle. Ambition without constraints is empty. Consistency without fertility is sterile. Fertility without contact becomes self-reference. The practical wisdom is to hold several virtues in tension and to let data mediate the pull. Theories should be internally consistent, externally coherent with what is known, predictive in a way that can fail, economical in assumptions, generous in consequences, and humble before measurement. No single program will score high on all fronts at all times. The portfolio view is healthier than the monolith. In the coming years, instruments will become quieter and wider, but they will not grant infinite reach. That fact does not absolve judgment, it sharpens it. Ideas must be written so that partial confirmation or partial disconfirmation teaches something even without a decisive blow. Proxy predictions, cross-checks across independent datasets, and robustness under perturbations become essential. Theories that fail gracefully are easier to learn from than those that hide their stakes behind the next scale. The final act is not a trial by beauty. It is a wager placed with care. A community selects projects to nurture because they compress well, because they cohere with many facts, because they generate tools, because they dare to expose themselves to being wrong, and because they give young minds something to do that ends with a number that can be compared. Beauty guides the hand that writes the bet. Truth is the croupier that sweeps the table clean or pushes the stack forward. The best players learn to admire the elegance of a lost round, then move to the next table with steadier hands. Night after night, instruments collect signals at the brink of silence, and day after day, analysts gather the harvest into disciplined ledgers. A pattern emerges that is larger than any one experiment. It is the long vigil of testing, not a single decisive blow, but a choreography of careful strikes that narrow possibilities and elevate what survives. Patience becomes methodology. The horizon is far, yet the path toward it is paved with choices that make refutation possible and confirmation meaningful. The first choice is to ask questions that nature can answer within finite means. Ambitious conjectures are translated into parameterized statements with clear fail conditions. Instead of betting everything on a single dramatic signature, collaborations develop ladders of predictions. The lowest rungs are proxy observables that lie within reach today. Slight drifts in timing, tiny cross-correlations between independent maps, small departures from textbook waveforms, each becomes a foothold. If a model has no such footholds, it is trimmed until it does, or it is set aside as poetry without method. A second choice is to test frameworks rather than monuments. Broad, effective descriptions capture many possibilities at once and let data crown or dismiss regions of theory space. Parameterized post-Newtonian expansions in the slow regime, generalized waveforms for compact mergers, and symmetry-based catalogues of violations provide neutral stages on which data can speak. The philosophy is simple. Do not ask nature to confirm our favorite story outright. Ask her whether any story with a given structure fits her numbers. When a region is ruled out, entire families of models fall with it. Large collaborations rehearse skepticism as a craft. Analyses are pre-registered so that outcomes do not silently reshape hypotheses. Blind injections are made to stress pipelines and protect against confirmation bias. Multiple teams analyze the same data with different tools and then compare results. Null streams are constructed that cancel real signals and leave only noise, a direct test of residual systematics. Internal reviews are adversarial by design. A claim that survives this gauntlet is not guaranteed to be true. It is guaranteed to have faced intelligent resistance. Statistics become instruments of their own. When signals are rare and weak, single detections may never rise above doubt, yet populations can. Hierarchical inference collects many modest events and stacks their information into sharp posteriors. Upper limits that once felt like shrugs become corridors that squeeze theory. Model comparison penalizes flexibility that only fits after the fact. Selection effects are not nuisances but parameters that must be inferred alongside the signal itself. The story is then honest about what the detectors could have seen, as well as what they did. Cross-checks are as important as first sightings. A polarization pattern that tempts in one map must appear in another, built from different frequencies and different instruments. A deviation in a gravitational waveform must recur across independent events with the same template of parameters. Timing anomalies in one pulsar must participate in a shared pattern across the sky before anyone speaks of a background. A signature that migrates with the data reduction recipe is not a signature. A signature that stays put while the analysis changes has earned the right to be called a clue. Foregrounds are adversaries that teach humility. Dust aligns and glows. Plasma disperses and refracts. Thermal gradients tilt beams. Seismic fields tug mirrors through Newtonian gravity. Instead of treating these as distractions, experiments turn them into measured fields. Foreground models are built from independent surveys. Auxiliary sensors map disturbances in the environment. Joint likelihoods marginalize over foreground parameters, so that uncertainty is accounted for rather than wished away. The cleanest result is not the one that subtracts the most. It is the one whose error bars tell the truth. Theory and experiment co-evolve in this vigil. When a constraint arrives, theorists refine the grammar of possibilities. When a new formal tool appears, experimentalists search their archives for the particular combination of observables that tool can sharpen. Modular predictions are preferred because they can be retired or advanced without toppling the whole program. A specific coupling, a narrow resonance, a forbidden correlation across scales, each can live or die on its own merits while the wider framework persists. Time itself is a collaborator. Some targets demand decades. Wide binaries unwind their secrets slowly. Backgrounds in the nanohertz band paint their patterns only after long timing baselines. Spectral distortions need many years of stable calibration. Projects accept that cadence and design milestones along the way. Interim deliverables include calibration papers, public data releases, and demonstrations of noise reduction that stand as contributions independent of headline claims. The culture prizes continuity. Instruments are upgraded rather than replaced, pipelines are versioned with care, and knowledge about subtle systematics is treated as a scientific result. Openness becomes a technology. Data that once would have been guarded for years are released with documentation and code. External teams reproduce key results and find their own. Community challenges invite blind analyses on shared synthetic sets. Reproducibility is no longer a slogan. It is a workflow, complete with containers, notebooks, and persistent identifiers that allow a figure to be regenerated with a single command. Trust grows when others can press the buttons and watch the same numbers appear. The vigil also knows when to say no. A tantalizing fluctuation that refuses to stabilize across seasons becomes a lesson in patience. An anomaly that tracks with ambient temperature or detector orientation is catalogued and used to improve design rather than paraded as a discovery. A theoretical idea that never translates into a measurable inequality is respected as metaphor and set to one side while instruments chase sharper prey. The refusal to overclaim is not modesty. It is the discipline that keeps the collective signal to noise high. Risks are budgeted like resources. Some fraction of effort is placed on wildcards, where a single observation could redirect the field. Another fraction works the safe edges where incremental gains accumulate. A final fraction invests in infrastructure whose benefits will be broad and lasting, regardless of what any one theory predicts. Young researchers are encouraged to diversify their portfolios, so that careers do not hinge on the fate of a single promise. The system does not eliminate risk. It manages it. Global coordination multiplies sensitivity. Correlated baselines reduce local noise. Shared calibration standards align independent observatories. Synchronized campaigns catch transients in multiple channels at once. When one region of the world sleeps, another watches, and a shared ledger records a continuous time series that individual teams could never assemble alone. International agreements smooth data rights and credit, making collaboration a normal mode rather than an exception negotiated anew each time. Interpretation remains restrained even when the numbers are kind. A deviation that fits a speculative model is also checked against mundane alternatives. Systematic errors are not ruled out by assertion but by demonstration. Theories are updated gently, with parameter posteriors rather than with proclamations. If confirmation comes, it comes by degrees. If it fails to come, the record of what was tried is preserved so that future attempts do not retrace the same dead ends. The slow pace does not dull the sense of wonder. A slope in a spectrum, a tiny non-zero correlation across 1,000 pixels, a phase shift consistent across a dozen events, each raises the hair on the arm of anyone who has waited through the long nights of quiet. The beauty is not only in the final number, but in the way it was earned. The culture of testing becomes its own art, with tools honed to subtlety and habits of thought tuned to hear the difference between rumour and report. In this vigil, truth is not a sudden trumpet. It is the faint accumulation of evidence that stands after wind and noise are subtracted, after biases are measured and removed, after friendly critics have tried every lever to break the claim. What remains is not flashy, it is reliable. From such reliability, new laws are made. From such patience, theory learns how to ask better questions. The horizon may stay far. The path toward it is already illuminated by the quiet light of careful tests. Evening gathers over domes of glass and aluminum, while a thin frost climbs the rails of deserted catwalks. Inside, instruments idle at their set points, small green lamps breathing like patient lungs. A quiet falls that is not absence, but readiness. The universe continues in its distant labour, and the listeners continue in theirs. Between them lies a distance that is both physical and human. It is crossed not by leaps, but by the slow practice of attention. Wonder is the most durable instrument. It needs no calibration, yet it improves with use. A single photon may prompt it. So might a carefully cancelled background, a null result whose precision rewrites what could have been. The feeling is not naivete. It is a measured astonishment that the world admits order at all, that equations written in chalk should nudge reality into revealing some of its habits. Each habit that is learned is a threshold that was crossed without ceremony, and yet with consequence. At such thresholds, imagination stands with a map that it drew before the border came into view. The map is provisional, sketched in lines of symmetry and hinted mechanisms. Some of those lines will become roads. Some will reveal cliffs. The value of the sketch is not that it is right, but that it is precise enough to be wrong in informative ways. A mind that thinks in models learns to fail forward, and to fail softly enough that the instruments remain the arbiters. There is dignity in hypotheses that will never be fully tested, provided they send measurable shadows into the domains that can be reached. A voice that speaks only of scales beyond all access asks for faith. A voice that offers a family of partial tests asks for patience. Between faith and patience lies the work of a century, a span long enough that individuals must hand the thread to those who follow. This relay is less a race than a craft. It inherits, discards, repairs, and leaves notes. The notes are sometimes equations and sometimes devices. A pattern recognized in amplitudes becomes a component in a detector. A trace of thermodynamics at a horizon becomes a clockwork for better timing. A new bound in a parameter space becomes a reason to change the curvature of a mirror or the coating of a lens. Theory and experiment are not rivals. They are two halves of a nervous system, sensation and inference, working toward a coherence that neither could manage alone. There are winters in this work, seasons when no anomaly ripens and no decisive signal arrives. The discipline required, then, is to understand the noise with as much love as the hoped-for signal. The hiss of resistors, the rustle of vacuum, the soft creep of glass under stress, the micrometer drift of a mount as it warms, each is a vocabulary word. Once learned, the word no longer confuses with what it is not. It becomes part of the world that is known, and the background against which the next whisper can be heard. Humility is not an ornament in this setting. It is a structural element. Without it, data are forced to bow to desire, and the edifice tilts. With it, a collaboration can say that a once promising trail is a cul-de-sac, and the admission raises rather than lowers the standing of the work. A field that lets itself be corrected is a field that will last. To build such a culture is more difficult than building an instrument. And more important, the future that is reachable is not an event but a vocabulary. Better clocks give more words for time. Wider arrays give more words for distance. Cooler masses and quieter cavities give more words for motion. With more words, subtleties can be named. With names, they can be counted. With counts, they can be predicted. The cycle seems simple. It is a high art, and the grammar it yields is the grammar in which reality agrees to be described. Speculation remains necessary even when it is trimmed. It keeps the questions alive that data alone cannot pose. It suggests designs that would not occur to an engineer starting from constraints. It invites mathematics to try structures that later become undeniably practical. The risk is not speculation itself. The risk is forgetting to return to measurement. When the return is made, the result is often not confirmation, but a new kind of curiosity, sharpened by limits and by an increased respect for detail. There is a human centre to all this machinery. A graduate student learns how to silence a ghost line that has crept into a spectrum. An observer notices that an unexpected correlation tracks the weather and not the cosmos. A theorist finds that an identity silently assumed by a generation fails under a change of variables that had not been tried. None of these acts arrives with trumpets. Each one is a stitch in a fabric that will keep its shape under strain. To speak of edges is to speak of horizons, and horizons are both physical and intellectual. A telescope may not resolve a source that it can still detect by its integrated glow. A calculation may not follow every degree of freedom, and yet can reach reliable asymptotics. There is courage in stopping where resolution becomes pretense. There is equal courage in inching forward when a small advance is honest and hard-won. Progress is not a march. It is a slow step work over mixed ground, sometimes sand, sometimes stone. A quiet thought threads through the laboratories. Perhaps nature is more generous than fear suggests, more intricate than hope expects, and more intelligible than either. The intelligibility is limited not by malice but by scale and by the cost of precision. No law prevents understanding. Resources do. That constraint is not nihilism. It is an invitation to ingenuity and to cooperation. When resources are shared, imagination finds new leverage. Instruments sleep, then stir. Another night is logged, another set of residuals inspected, another corner of parameter space painted with the grey of exclusion or the faint colour of possibility. The ledger grows, and with it the clarity that comes only from many small truths held together. Where the ledger remains blank, wonder remains useful. It keeps attention light enough to follow hints without breaking them, and steady enough to avoid chasing noise. It keeps gratitude near the surface for the simple fact that the cosmos answers at all. In that gratitude lies the healthiest kind of faith. Not faith that any one story will prevail, but faith that careful stories will be rewarded with clearer questions. The reward is sometimes a number and sometimes a design, sometimes a cancellation that simplifies a sum, and sometimes a leftover term that becomes the seed of discovery. The reward is always more to learn. A culture that loves that reward will not run out of work. What remains at the end of a long night are the same things that were present at the beginning. A sky whose light arrives late and yet on time. apparatus that transforms that light into data. Minds that translate the data into patterns and the patterns into tests, a willingness to be wrong, a taste for being surprised, a quiet confidence that the world is lawful enough to merit another night. That confidence is not naivete, it is the conclusion of many nights well spent, and the reason to switch on the lamps again. The building exhales as the heaters click, and frost retreats from the handrail like a thought withdrawing. A thin moon rests above the ridge. Far away, a river folds itself through a valley that no instrument will map in detail, and yet the mind accepts its meander as part of the same ledger that holds galaxies. In that acceptance lives the calm that makes inquiry possible. It knows that most of existence is quiet, that meaning is found not only in the rare flare of discovery, but in the long patience that puts the flare in context. Glass and gold and vacuum work their small miracles, and behind them people do, too, the way caretakers move through sleeping rooms without waking anyone. A loose screw is tightened, a line is rerouted so it does not hum, a script is made kinder to the next pair of eyes. These uncelebrated acts keep the instruments honest. They also keep the community human. The stairs creak with footsteps that will return tomorrow, and the day after that, carrying coffee, carrying questions, carrying the ordinary courage to start again. Above the domes, the sky remains a dark lake carried in a bowl too large to imagine. Stars roughen its surface. A satellite writes a brief scratch that fades. Somewhere in that dark, a beam passes through a place so curved that light scarcely knows which way is straight, and a detector on Earth receives the tremor. The receiving is the humble half of wonder. It says yes to what arrives, without insisting that arrival be spectacular. If there is a benediction suitable for such work, it is simple. May curiosity stay soft but stubborn. May instruments stay quiet and precise. May arguments be frank and kind. May the nights be long enough to hear what is faint, and the mornings generous enough to let what was heard be questioned. The rest is the slow mercy of comprehension, which comes when it will, and stays only as long as it is earned. End of script. Sweet dreams.